If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. A glimpse through the hourglass. Imagine standing on the precipice of eternity, peering through the veil of time itself. In that moment, the line separating past, present, and future dissolves into a vast continuum, flowing like a river winding through the cosmos. For millennia, humanity has gazed into the heavens, not merely to understand where we are, but to grasp when we are. Time, that invisible thread tying together our experiences, has always tantalized us with the question, can we travel through it? And if we can, what lies on the other side of the hourglass? The concept of time travel ignites something primal in the human imagination. It is the ultimate form of exploration, an odyssey not just across uncharted landscapes, but across the epochs of existence itself. Ancient myths spoke of individuals who bent the rules of time, stepping back into the mists of history or leaping ahead into unknown tomorrows. These legends planted the seeds of a timeless fascination that science would later begin to nurture. To unravel the mystery of time travel, we must first understand time itself. Unlike the air we breathe or the stars we see, time cannot be touched, weighed, or even directly observed. Yet, it governs every moment of our existence. What if time is not an unyielding constant, but something fluid, malleable, and capable of being reshaped? This notion isn't just a fantasy. It's a scientific hypothesis born from some of the most brilliant minds in human history. Picture a star millions of light years away, its light taking eons to reach our eyes. As we look at it tonight, we are peering into the past, seeing it as it was long before the first humans walked the earth. In this sense, telescopes are our first primitive time machines, showing us fragments of history frozen in light. But could we do more than observe the past? Could we touch it, interact with it, or even alter it? The first steps toward answering these questions began with Albert Einstein. His groundbreaking theory of general relativity revealed that time is not an independent entity, but is intertwined with space, forming the fabric of the universe, space-time. This revelation shattered the old Newtonian view of time as a universal constant, ticking steadily forward like a cosmic clock. Instead, Einstein showed us that time can stretch, compress, and warp depending on the gravitational forces acting upon it. This discovery wasn't just theoretical. Experiments proved that time dilation, a phenomenon where time moves slower for objects in stronger gravitational fields or at high velocities, is real. Astronauts aboard the International Space Station, for instance, experience time at a slightly slower rate than those of us on Earth's surface. While the effect is minuscule, it hints at something profound. Time is not fixed, and if it can be stretched or compressed, could it also be reversed or looped? Here's where our story deepens. The very fabric of the universe may hold the key to traveling through time, but bending it requires immense energy and an understanding of physics that, for now, remains just out of reach. Imagine space-time as a massive sheet of fabric. Place a heavy object, like a bowling ball, on the sheet, and it creates a depression. Smaller objects roll toward it, illustrating how gravity works. Now, envision twisting that fabric into a loop, connecting one part to another. Theoretically, such a loop could serve as a bridge across time itself. This bridge isn't just a metaphor. Physicists call these hypothetical pathways wormholes, shortcuts through space-time that might connect distant points in the universe, or even different times. Wormholes, if they exist, could be the linchpin of time travel. Yet they come with challenges that seem almost insurmountable. Could we keep one open long enough to travel through it? What would happen to someone or something on the other side? And most intriguingly, could these pathways already exist naturally within the universe? The idea of wormholes and time travel isn't confined to dusty theoretical papers. It has sparked cultural revolutions, inspiring novels, movies, and countless late-night debates. From H.G. Wells' The Time Machine to the blockbuster worlds of Interstellar and Doctor Who, the notion of stepping outside time continues to grip the collective consciousness. But the science behind these tales is no less fascinating than the stories themselves. Each step we take toward understanding time's mysteries brings us closer to answering one of humanity's oldest dreams. What if we could rewrite our past or witness our distant future? As we embark on this journey through the physics, philosophy, and paradoxes of time travel, remember that every second ticking away isn't just a measure of time passing. It's a reminder of our place within an infinite cosmos. And as we dive deeper into this cosmic enigma, one question will persist. If time is but a river, can we learn to swim against its current? Or will we forever remain at its mercy, swept along the flow of an unchangeable present? The fabric of space-time. To understand the potential of time travel, we must first unravel the universe's deepest architecture, the fabric of space-time. Imagine the cosmos as a vast, invisible grid that stretches infinitely in all directions. Every star, every planet, and every atom exists within this grid, its movement and behavior governed by the unseen threads weaving space and time together. This is not merely a poetic concept. It is a tangible framework described by the revolutionary ideas of Albert Einstein, who forever altered our understanding of reality. In 1915, Einstein introduced his theory of general relativity, which described gravity not as a force pulling objects together, but as the warping of space-time caused by mass. Picture a trampoline with a heavy ball placed in the center. The surface sags, and smaller objects roll toward the depression. In this analogy, the ball represents a celestial body like the sun, and the surrounding curvature is the gravitational field that keeps planets in orbit. However, Einstein's insight went further. Time, he proposed, is not separate from space but is intertwined with it, creating a single, four-dimensional entity, space-time. This revelation introduced an extraordinary possibility. If space-time is a fabric, it can theoretically be bent, twisted, or folded. In a flat universe, traveling from point A to point B might take eons, but if space-time could be folded so that the 2 points touched, the journey would be instantaneous. This is the principle behind wormholes, hypothetical tunnels connecting distant points in the universe, and perhaps different moments in time. But bending space-time isn't just about shortcuts across galaxies. It's also about manipulating time itself. Gravity, as Einstein revealed, doesn't just distort space, it slows time. The stronger the gravitational field, the slower time flows relative to an observer in a weaker field. This effect, known as time dilation, has been confirmed by countless experiments. For instance, highly accurate atomic clocks placed on airplanes tick slightly slower than those on the ground, demonstrating the tangible effects of gravity on time. Now let's scale this concept to cosmic proportions. Imagine standing near the event horizon of a black hole, a region where gravity becomes so intense that not even light can escape. Time near this boundary would crawl compared to the time experienced by someone farther away. For an observer, a minute near the event horizon might equate to hours or even years in the wider universe. The closer you approach the black hole, the slower time becomes, until at the singularity, the black hole's infinitely dense core, time ceases entirely. Such phenomena are not mere curiosities. They are evidence of time's malleability, hinting at the potential for traversing it. The malleability of space-time leads to an intriguing possibility: closed time-like curves, CTCs. These are theoretical paths through space-time that loop back on themselves, allowing an object or person to return to their own past. While these curves sound like science fiction, they emerge naturally from Einstein's equations under certain conditions. For instance, if a massive object rotates rapidly enough, it could theoretically twist space-time into a spiral, creating a path that circles backward in time. This idea forms the basis for some speculative designs of time machines, like the Tipler cylinder, a hypothetical construct involving a massive, infinitely long cylinder spinning at near-light speeds. However, such constructs are not without their challenges. The energy requirements for creating and maintaining a closed time-like curve are staggering, far beyond anything humanity can currently produce. Furthermore, the introduction of quantum mechanics, the science governing the behavior of subatomic particles, complicates matters. Quantum physics and general relativity often clash, creating inconsistencies when applied to extreme scenarios like time travel. Resolving these conflicts is one of the greatest challenges in modern physics, and it has led to the pursuit of a theory of everything that could unify the two frameworks. But even if we could bend space-time at will, there's another question to consider. What happens to causality, the principle that cause precedes effect? In our everyday experience, events follow a linear progression. A ball rolls because we pushed it. But in a universe with closed time-like curves, the distinction between cause and effect could blur, creating paradoxes. For instance, what if you traveled back in time and prevented your own birth? Would you cease to exist? And if so, who traveled back to stop it? Physicists have proposed several ways to resolve these paradoxes. One idea is the Novikov self-consistency principle, which suggests that events in a time travel loop must be consistent with one another. In other words, even if you traveled back to change the past, your actions would always align with the present you came from. Another theory involves the multiverse, positing that each change to the past creates a new, parallel timeline, leaving the original timeline intact. While these theories remain speculative, they highlight the profound implications of bending space-time. It's not just about exploring distant stars or revisiting historical moments. It's about challenging the very nature of reality. If space-time is as flexible as Einstein's equations suggest, then the universe may be far stranger and more interconnected than we ever imagined. The idea of space-time as a fabric opens up tantalizing possibilities. Could there already be natural shortcuts, wormholes, hidden in the vast expanse of the cosmos? Are there regions where the flow of time deviates so drastically that they act as natural time machines? And most provocatively, could we one day learn to manipulate this fabric, stitching together the past, present, and future into a unified whole? These questions remind us that space-time is not just a scientific concept. It is the stage on which the drama of existence unfolds. And as we journey deeper into its mysteries, we must confront not only the physical challenges of time travel, but also its philosophical and ethical implications. For if we can bend the fabric of space-time, what responsibilities come with holding the threads of the universe in our hands? The enigma of wormholes. As we venture deeper into the mysteries of time travel, one concept stands out as a potential key to unlocking the secrets of both the cosmos and the flow of time: wormholes. These theoretical tunnels through space-time represent the intersection of imagination and cutting-edge physics, a bridge between distant points in the universe, or perhaps even different eras. But what exactly are wormholes, and could they truly exist within the framework of reality? To understand wormholes, let us revisit the fabric of space-time. Imagine the universe as a two-dimensional sheet of paper. Now, draw two dots on opposite ends of the paper and fold the sheet so the dots touch. This folding represents the wormhole, a shortcut that bypasses the vast distances between the 2 points. Unlike the traditional notion of traveling through space linearly, a wormhole compresses the journey into an instant connection. The theoretical foundation for wormholes comes from Einstein's general relativity, specifically a solution to his equations known as the Einstein-Rosen bridge. In 1935, Einstein and his colleague Nathan Rosen proposed the existence of these bridges as a way to connect separate regions of space-time. Originally conceived as a mathematical curiosity, wormholes have since become a cornerstone of speculative physics, igniting countless debates and hypotheses about their potential reality and applications. A wormhole consists of two mouths and a throat connecting them. These structures would allow matter, or even information, to travel between the mouths, bypassing the intervening space. In theory, if one end of the wormhole were positioned near a strong gravitational field or moved at near light speeds, time dilation could occur. This could make one end of the wormhole older or younger than the other, effectively turning it into a portal through time. However, the existence of wormholes is not without significant challenges. First, their stability is a major concern. Wormholes are predicted to collapse almost instantaneously under their own gravity, snapping shut before anything could pass through. To counteract this, physicists have proposed the use of exotic matter, a hypothetical substance with negative energy density that could exert a repulsive force, preventing the wormhole from collapsing. Exotic matter is not entirely beyond the realm of possibility. Phenomena like the Casimir effect, where vacuum fluctuations produce negative energy between two plates, hint at its existence. Yet, scaling such effects to the cosmic level remains a monumental task. Even if we could stabilize a wormhole, the question of traversability arises. Would traveling through a wormhole be a smooth experience? Or would the intense gravitational forces and tidal effects destroy anything attempting passage? Simulations suggest that the journey could be perilous, as the structure of the wormhole might distort and twist violently. Protecting travelers from these forces would require breakthroughs in materials science and an understanding of physics far beyond our current capabilities. The search for wormholes isn't just theoretical. Astrophysicists have speculated that certain phenomena in the universe might signal the presence of these cosmic shortcuts. For instance, peculiar gravitational lensing effects, where light from distant stars bends around massive objects, could potentially hint at the existence of a wormhole. Similarly, anomalous emissions or distortions in space-time might betray their presence. While no definitive evidence has been found, the possibility continues to drive scientific curiosity. One of the most compelling aspects of wormholes is their potential to connect not only distant regions of space but also different points in time. This possibility arises from the flexibility of space-time itself. If one mouth of a wormhole experienced intense time dilation, the two ends could become desynchronized, effectively turning the wormhole into a time machine. Such a mechanism could theoretically allow someone to step into one end and emerge in the past or future. But what about the paradoxes? Using a wormhole for time travel introduces the same mind-bending dilemmas that plague all temporal theories. For example, what would prevent someone from traveling back in time and altering the events that led to the creation of the wormhole itself? Physicists often address these paradoxes with concepts like self-consistency, which ensures that any actions taken in the past are already accounted for in the present, or the multiverse hypothesis, where changes to the past spawn entirely new timelines, leaving the original timeline unaffected. Speculative as they may seem, wormholes have captured the imagination of both scientists and storytellers. In popular culture, they often serve as the ultimate plot device, enabling interstellar travel, time travel, and even encounters with alternate realities. Films like Interstellar and Contact explore the emotional and philosophical implications of wormholes, while series like Stargate turn them into tools for adventure. These depictions often simplify or exaggerate the science, but they underscore the enduring allure of the concept. Beyond their theoretical implications, wormholes raise profound philosophical questions. If they exist, who or what created them? Could they be natural phenomena, forming spontaneously in the chaotic interplay of cosmic forces? Or might they be the handiwork of advanced civilizations, engineered to navigate the vastness of space and time? And if they are artificial, what would it mean for humanity to discover and harness such technology? Even without definitive answers, the study of wormholes pushes the boundaries of human understanding. They challenge us to think beyond the constraints of our everyday experiences, to imagine a universe where the impossible becomes possible. And in doing so, they remind us that the cosmos is far stranger and more wondrous than we can yet comprehend. As we continue our exploration of time travel, wormholes stand as a tantalizing possibility, a doorway to realms unknown. But the road to harnessing such power is fraught with obstacles, both scientific and philosophical. What lies on the other side of these cosmic bridges? And if we ever step through, will we emerge as the same beings who took the first daring step? Building a time machine? The idea of constructing a time machine sounds like pure science fiction, a fantastical dream plucked from the pages of H.G. Wells or the dazzling sequences of Hollywood blockbusters. Yet, within the realms of theoretical physics, scientists have dared to ask, what would it take to turn this dream into a reality? Could we build a device that manipulates the fabric of space-time, allowing us to step into the past or leap into the future? To embark on this audacious journey, we must first understand the principles underlying any potential time machine. At its core, the challenge is to exploit the flexibility of space-time, bending it in such a way that different moments, past, present, and future, can converge. While this might sound like fantasy, theoretical models offer tantalizing clues about how such manipulation might be achieved. One of the most discussed mechanisms for time travel is the creation of a closed time-like curve, CTC. This is a path in space-time that loops back on itself, allowing an object to return to its own past. To create a CTC, we would need to bend space-time so drastically that it forms a loop connecting 2 points in time. But how can such extreme warping be accomplished? Enter the concept of rotating massive objects. In 1949, mathematician Kurt Gödel proposed a solution to Einstein's equations that suggested a universe filled with rotating matter could create closed time-like curves. The intense rotational motion would twist space-time into spirals, making it theoretically possible to travel back along the curve. While Gödel's model applies to an entire universe, some physicists have speculated that a smaller-scale version could be engineered using a rapidly spinning, supermassive object, perhaps even an artificial structure. This idea inspired the Tipler cylinder, a hypothetical time machine proposed by physicist Frank Tipler in 1974. The Tipler cylinder would consist of a massive, infinitely long cylinder spinning at near-light speeds. The rapid rotation would twist space-time around the cylinder, creating closed time-like curves. While intriguing, this concept has significant limitations. For one, constructing an infinitely long cylinder is beyond our capabilities, and our universe may not even allow such a structure to exist. Even if we could build a finite version, the energy required to achieve the necessary rotation would be astronomical. Another approach involves using wormholes as time machines. As discussed earlier, wormholes are theoretical tunnels through space-time, potentially connecting distant points in both space and time. If one mouth of a wormhole were placed near a strong gravitational field or moved at high speeds, time dilation could cause it to experience time differently than the other mouth. This time discrepancy could turn the wormhole into a time portal, allowing someone to step through and emerge at a different moment in time. To make this work, however, we would need to solve the problem of wormhole stability. Wormholes, if they exist, are predicted to collapse almost instantly under their own gravity. Keeping one open would require exotic matter, a substance with negative energy density that could counteract the gravitational forces. While exotic matter is a purely theoretical construct, its existence is not entirely ruled out by the laws of physics. Phenomena like the Casimir effect, where negative energy arises between two closely placed plates, hint at the possibility of creating such material, though on a vastly smaller scale. Even with a stable wormhole, practical challenges remain. The intense gravitational forces within the wormhole could destroy anything attempting to pass through. Moreover, navigating the wormhole would require precise calculations to avoid becoming trapped or lost in space-time. Developing such a navigation system would demand advances in both physics and computational technology far beyond what we possess today. A third concept for building a time machine involves using black holes. As massive objects that warp space-time to its extreme, black holes naturally slow down time near their event horizons. By orbiting close to a black hole, without crossing the event horizon, a spacecraft could experience significant time dilation. For the crew aboard the ship, only a few hours might pass, while years could elapse for an observer farther away. This principle, illustrated in the movie Interstellar, offers a form of one-way time travel into the future. However, using black holes as time machines comes with immense risks. The gravitational forces near the event horizon are so intense that they could spaghettify any object venturing too close. Additionally, the logistics of traveling to and from a black hole, which are often located thousands of light years away, present another significant obstacle. Perhaps the most futuristic idea for a time machine involves harnessing quantum mechanics. Quantum phenomena, such as superposition and entanglement, suggest that particles can exist in multiple states or locations simultaneously. Some physicists have speculated that these principles could be extended to larger scales, creating a device that exploits quantum effects to manipulate time. For instance, a quantum time machine might use the phenomenon of quantum tunneling, where particles jump across barriers to bypass the normal flow of time. But quantum time machines face their own theoretical hurdles. For one, they require a deeper understanding of how quantum mechanics interacts with general relativity, two frameworks that are notoriously difficult to reconcile. Moreover, scaling quantum effects to macroscopic levels would involve levels of precision and control that are currently unimaginable. If the physical challenges of building a time machine weren't daunting enough, the ethical and philosophical implications add another layer of complexity. What responsibilities come with the ability to alter the past or glimpse the future? Could such power be wielded without catastrophic consequences? And who would control such technology, deciding how and when it should be used? Despite these challenges, the quest to build a time machine continues to inspire scientists and dreamers alike. Even if practical time travel remains out of reach, the pursuit of these ideas pushes the boundaries of human understanding, forcing us to rethink the nature of reality and our place within it. At its heart, the dream of building a time machine is about more than just escaping the present or revisiting the past. It is a testament to humanity's unyielding curiosity, our desire to explore not just the physical universe, but the very fabric of existence. And as we ponder the possibilities, one question lingers. If we could build a time machine, would we dare to use it? Or would the knowledge of what lies ahead, or behind, prove too much for us to bear? Paradoxes and loopholes. The prospect of time travel tantalizes us with possibilities, revisiting cherished moments, correcting mistakes, or witnessing the wonders of the future. Yet, the deeper we delve into the concept, the more apparent it becomes that time travel is not just a technological challenge, but also a philosophical and logical puzzle. Time travel introduces paradoxes, logical contradictions that seem to defy the very fabric of reality. But do these paradoxes make time travel impossible, or could there be hidden loopholes within the laws of the universe? Let's begin with one of the most famous and mind-bending paradoxes, the grandfather paradox. Imagine a time traveler journeying into the past and accidentally, or intentionally, preventing their grandfather from meeting their grandmother. If the grandfather never has children, the time traveler would never be born, making their trip back in time impossible. Yet, if the trip never happened, the grandfather would remain unharmed, the time traveler would be born, and the cycle would repeat endlessly. This paradox creates a logical contradiction that seems to make backward time travel inherently problematic. Physicists have proposed several ways to resolve the grandfather paradox. One potential solution is the Novikov self-consistency principle, which suggests that events in a time travel loop must be self-consistent. In other words, any action taken by a time traveler would already be part of history and could not create contradictions. For instance, if you went back in time to prevent your grandfather's marriage, some unforeseen circumstance, perhaps a chance meeting, might still lead to your grandparents' union, ensuring your existence. In this view, the universe protects itself from paradoxes by preventing actions that would disrupt causality. Another intriguing resolution involves the many worlds interpretation of quantum mechanics. This theory posits that every decision or event creates a branching timeline, forming a multiverse of parallel realities. If you travel back in time and change the past, you would not alter your original timeline, but create a new, parallel one. In this scenario, the grandfather paradox is avoided because both timelines coexist independently. However, this raises a profound question. If time travel only affects alternate realities, can it truly be considered time travel, or is it simply a way of exploring parallel universes? Beyond the grandfather paradox, other scenarios reveal the logical pitfalls of time travel. Consider the bootstrap paradox, also known as the ontological paradox. In this scenario, an object or piece of information exists in a time loop with no clear origin. For example, imagine a scientist who receives the plans for a revolutionary invention from a time traveler. The scientist builds the device and later uses the time machine to travel back and deliver the plans to their younger self. In this loop, the plans seem to exist without ever being created, defying our understanding of cause and effect. Where then did the plans originate? The bootstrap paradox challenges our notions of time as a linear progression and suggests that some events might exist outside conventional causality. Another perplexing scenario involves predestination paradoxes, where time travel appears to lock events into an unchangeable cycle. Imagine trying to prevent a historical tragedy, only to discover that your actions were the very catalyst for the event. In this case, your intervention doesn't change the past, but ensures that it unfolds as recorded. Predestination paradoxes imply that even with time travel, free will may be an illusion, as all actions are predetermined by the timeline. These paradoxes are not just abstract thought experiments. They expose the fragility of our understanding of time and causality. Yet, some physicists argue that these contradictions might not be fatal to the concept of time travel. Instead, they could point to deeper truths about the universe. For example, closed time-like curves, CTCs, which are theoretical paths through space-time that loop back on themselves, naturally give rise to paradoxes. However, some models of CTCs, such as those based on the Novikov self-consistency principle, suggest that the universe could inherently prevent paradoxes by restricting possible actions within the time loop. Alternatively, the laws of physics might impose chronology protection, a concept proposed by Stephen Hawking. Hawking speculated that the universe might have mechanisms, such as quantum effects, that prevent time travel to the past altogether, thereby avoiding paradoxes. This idea, known as the chronology protection conjecture, aligns with our current inability to observe or detect evidence of time travelers. If backward time travel is impossible, the universe would remain free of paradoxes, maintaining the integrity of causality. But what about loopholes? Could there be ways to sidestep paradoxes and navigate time without disrupting causality? One potential loophole involves one-way time travel. Traveling into the future, as opposed to the past, avoids most paradoxes because it does not interfere with established events. Time dilation, as predicted by Einstein's theory of relativity, already allows for one-way time travel. For example, astronauts traveling at near light speeds would experience time more slowly than those on Earth, effectively leaping into the future. Another loophole might involve restricted time travel, where the ability to alter events is limited by physical or logical constraints. For instance, a time traveler might be able to observe the past without interacting with it, like a cosmic spectator. This concept is often depicted in science fiction as a way to preserve the timeline while still allowing for temporal exploration. The multiverse hypothesis also offers a potential escape from paradoxes. If time travel creates new timelines, travelers could theoretically make changes without affecting their original reality. However, this raises philosophical questions about identity and responsibility. If a traveler alters a parallel timeline, are they morally accountable for the consequences, even though their original timeline remains unaffected? Time travel paradoxes also force us to reconsider the nature of time itself. Is time a linear sequence of events as we commonly perceive it, or could it be more like a landscape, where all moments coexist simultaneously? Some physicists, inspired by the block universe model, argue that the past, present, and future are all equally real, existing as a four-dimensional block of space-time. In this view, time travel might simply involve moving through the block in unconventional ways, rather than rewriting its contents. As we grapple with these paradoxes, it becomes clear that time travel is as much a philosophical challenge as it is a scientific one. The contradictions it introduces force us to confront profound questions about free will, causality, and the nature of reality. Could the universe accommodate the seemingly impossible? Or do the paradoxes of time travel reveal the limits of our understanding? Despite the daunting complexities, the exploration of time travel paradoxes drives us to think more deeply about the cosmos and our place within it. Each paradox, rather than being an insurmountable barrier, serves as a gateway to new ideas and possibilities. As we continue to probe the mysteries of time, we are reminded that the universe, in all its intricacy, may still hold answers that defy our expectations. Black holes and time dilation. Deep in the cosmos lie regions of unimaginable power and mystery. Black holes, the gravitational titans of the universe. These enigmatic phenomena are more than just cosmic vacuum cleaners. They are gateways to some of the most profound effects in physics. Among their many astonishing properties is their ability to warp time itself. If time travel to the future is possible anywhere in the universe, black holes may hold the key. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. The result is a singularity, a point of infinite density where the known laws of physics break down. Surrounding this singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. But it's not just space that is distorted near a black hole. Time is equally affected. The extreme gravitational pull of a black hole slows down time in a phenomenon known as gravitational time dilation. To understand gravitational time dilation, imagine a clock ticking far from any massive object. Its rhythm remains steady, unaffected by gravitational forces. Now place the clock near a black hole. As the black hole's immense gravity bends space-time, it also stretches time itself, causing the clock to tick more slowly. To an observer far from the black hole, time near the event horizon appears to move at a crawl. Conversely, for someone near the black hole, their perception of time feels normal, even though the outside universe is racing forward. This effect, predicted by Einstein's theory of general relativity, has been confirmed through observations and experiments. One of the most famous examples involves satellites in Earth's orbit. The weaker gravity at higher altitudes causes onboard atomic clocks to tick slightly faster than identical clocks on the ground. This same principle, magnified to an extreme degree, operates near a black hole, where time dilation becomes so pronounced that hours near the event horizon could correspond to years or centuries elsewhere. Consider a hypothetical scenario. An astronaut ventures close to the event horizon of a black hole, spending only a few hours in its vicinity. Upon returning to their spacecraft, they might find that decades have passed for their crewmates who remain farther away. This phenomenon, while astonishing, is not merely theoretical. It was vividly portrayed in the movie Interstellar, where the crew of a spaceship experiences severe time dilation while exploring a planet near a supermassive black hole. For them, minutes equate to years back on Earth, a dramatic but scientifically plausible depiction. Black holes also inspire speculation about their potential use as one-way time machines into the future. If an advanced civilization could navigate near a black hole without crossing the event horizon, they could harness its extreme time dilation to leap forward in time. However, the dangers are immense. The intense gravitational forces near the event horizon create tidal effects so powerful they could spaghettify any object, stretching it into thin strands. Surviving such conditions would require technology far beyond our current capabilities. But what about traveling to the past? This is where black holes become even more enigmatic. Some solutions to Einstein's equations suggest that rotating black holes, also known as Kerr black holes, might harbor wormholes or even time loops within their structure. These hypothetical features could, in theory, allow travel to different points in time. However, the stability of such pathways remains highly questionable. Even slight perturbations, such as the presence of a particle or photon, might collapse the wormhole or disrupt the time loop, rendering it unusable. Adding to the mystery are white holes, the theoretical counterparts to black holes. While black holes pull matter in, white holes are predicted to expel it, acting as sources of matter and energy rather than sinks. Some physicists speculate that white holes could be linked to black holes via wormholes, creating a passage through space-time. If such connections exist, they might enable travel not only across vast cosmic distances but also across time itself. Yet, no observational evidence of white holes has been found, leaving them as intriguing but unproven concepts. Beyond their potential as time machines, black holes also challenge our understanding of time at the most fundamental level. Near a black hole, the distinction between past, present, and future begins to blur. For an observer falling into a black hole, time might appear to stretch infinitely as they approach the singularity. To an outside observer, however, the falling object would seem to freeze at the event horizon, never actually crossing it. This dual perspective highlights the relativity of time and underscores the strange, almost paradoxical nature of black holes. Perhaps the most tantalizing question about black holes is whether they could reveal deeper truths about the nature of time itself. The singularity at the heart of a black hole represents a breakdown in our understanding of physics, where general relativity and quantum mechanics clash. Reconciling these two frameworks, creating a theory of quantum gravity, might unlock new insights into the behavior of time under extreme conditions. Could the singularity, rather than being a dead end, be a gateway to a deeper understanding of the universe? Or might it harbor secrets that could one day make time travel a reality? As we continue to study black holes, we uncover more about their profound influence on space, time, and matter. Observations of black hole mergers, detected through gravitational waves, have already begun to test the limits of our theories. Projects like the Event Horizon Telescope, which captured the first ever image of a black hole shadow in 2019, bring us closer to understanding these cosmic phenomena. With each discovery, black holes transition from enigmatic monsters to laboratories for exploring the universe's most fundamental questions. Ultimately, black holes remind us that time is not a rigid constant, but a dynamic, malleable dimension shaped by gravity. They challenge us to think beyond our everyday experiences and confront the possibility that time, like space, is a landscape we have only begun to map. And as we stand on the threshold of these discoveries, one question looms. If black holes offer a glimpse into the future of time travel, will humanity ever muster the courage and the knowledge to step closer to the event horizon and peer into the unknown? Have you ever looked at the sky and felt the desire to understand your place in the universe? On Beyond the Stars, every video is a window to infinity, a journey to connect you with the mystery and beauty of the cosmos. Subscribing to the channel is more than clicking a button. It's joining a movement to spread knowledge and inspire others to look at the stars with hope and curiosity. Be the light that guides others to discover the wonders of the universe. Subscribe, and let's explore the unknown together. Quantum mechanics and time travel. While black holes and general relativity reveal time's malleability on a cosmic scale, the microscopic world governed by quantum mechanics presents an entirely different realm of possibilities for time travel. Quantum mechanics, the science of the very small, challenges our classical understanding of reality with principles that defy intuition. At its core, quantum theory suggests that particles can exist in multiple states simultaneously, influence each other instantly across vast distances, and even navigate through barriers they shouldn't be able to pass. Could these bizarre behaviors hold the key to unlocking time travel? To explore this question, we must delve into the fundamental principles of quantum mechanics. One of the most striking features of this realm is superposition, the idea that particles such as electrons or photons can exist in multiple states at once. For example, a particle might simultaneously occupy two different positions or spin in opposite directions. It's only when the particle is observed or measured that it chooses a specific state, collapsing the superposition into a single outcome. Superposition raises profound questions about the nature of time. In the quantum world, the past and future may not be as fixed as they seem. Some physicists propose that quantum systems could allow information, or even particles, to traverse time in ways that appear impossible in the macroscopic world. Imagine a particle that interacts with its own past or future self, creating a loop in time. Such interactions could potentially form the basis of quantum time travel. Closely tied to superposition is entanglement, another quantum phenomenon that challenges our understanding of causality. When two particles become entangled, their properties become linked, regardless of the distance between them. A change to one particle instantly affects the other, a phenomenon Albert Einstein famously called spooky action at a distance. This instantaneous connection seems to defy the limitations of the speed of light and suggests that information could, under the right circumstances, travel faster than time allows in classical physics. Could entanglement be used to transmit information across time? Some researchers believe it's possible. If two particles are entangled and one is manipulated in a way that affects its temporal properties, it might enable communication with the past or future. While this idea remains speculative, it underscores the potential for quantum mechanics to challenge the linear flow of time. One of the most intriguing applications of quantum mechanics to time travel involves quantum tunneling. In classical physics, particles cannot cross energy barriers that exceed their energy. Yet, in the quantum world, particles can tunnel through barriers, appearing on the other side without ever crossing it in the traditional sense. This phenomenon occurs because, at the quantum level, particles behave as waves of probability, spreading across space and allowing for the possibility of being in seemingly forbidden locations. Quantum tunneling suggests that particles might bypass the usual constraints of time and space. In theory, if we could harness and scale this effect, it might allow for shortcuts through time, similar to how wormholes provide shortcuts through space-time. While this remains firmly in the realm of speculation, tunneling offers a glimpse of how quantum principles could one day be applied to macroscopic systems, potentially enabling time travel. Another quantum concept with profound implications for time travel is the closed time-like curve, CTC. Proposed by physicist David Deutsch, this idea suggests that quantum particles might naturally exist in loops through time without creating paradoxes. According to Deutsch's model, quantum mechanics allows for the possibility of time travel because it inherently incorporates multiple timelines. A particle traveling along a CTC would essentially explore all possible outcomes, ensuring that its journey is consistent with the universe's quantum rules. Deutsch's work also hints at a resolution to the paradoxes that plague classical time travel. In the quantum realm, the many-worlds interpretation suggests that every event spawns a new branch of reality, forming a multiverse. If this is true, a quantum time traveler might not change their original timeline, but instead create or access a parallel one. This would sidestep issues like the grandfather paradox, as any changes to the past would occur in an alternate reality. But could quantum mechanics allow for time travel that affects our own timeline, rather than branching into parallel ones? Some scientists have explored the concept of retrocausality, where the effects of a quantum event influence its cause. For example, in certain experiments, the measurement of a particle seems to affect its state retroactively, as if the particle knew what would happen in the future. If this effect could be harnessed, it might allow for limited communication or interaction with the past. Quantum time travel, however, is not without its challenges. The scale at which quantum effects operate is extraordinarily small, and scaling these effects to macroscopic objects, or people, presents immense technical hurdles. Moreover, our current understanding of quantum mechanics and general relativity is incomplete. The two frameworks describe the universe in fundamentally different ways, and reconciling them into a unified theory of quantum gravity remains one of the greatest challenges in physics. Despite these obstacles, quantum mechanics continues to push the boundaries of our understanding of time. Experiments like the delayed choice quantum eraser, where the behavior of particles seems influenced by future measurements, hint at a reality where time is far less linear than it appears. Similarly, studies in quantum computing, which leverage superposition and entanglement, are already demonstrating how quantum principles can revolutionize technology and information processing. Could these advances one day lead to practical time manipulation? The intersection of quantum mechanics and time travel also raises profound philosophical questions. If time is not linear, what does that mean for our perception of free will? If particles can influence their own pasts, do we have the ability to shape our destinies? Or are all events predetermined by the quantum structure of the universe? And if the multiverse exists, does every decision we make create a new branch of reality, effectively making us time travelers within our own quantum minds? While the answers to these questions remain elusive, the exploration of quantum mechanics and its relationship to time reminds us of the universe's inherent strangeness. It challenges us to think beyond the constraints of classical physics and embrace a reality where the impossible might just be possible. As we continue to unlock the secrets of the quantum world, we may find that time travel is not merely a dream, but a fundamental aspect of the cosmos, waiting to be understood. The arrow of time. As we journey deeper into the mysteries of time, one question stands out. Why does time seem to move in a single direction? This one-way flow, from the past to the future, is what we call the arrow of time. It governs our perception of reality, shapes the unfolding of events, and gives structure to our lives. Yet, when we examine the laws of physics, we find a puzzling contradiction. Time doesn't have to move forward. So why does it? In most physical equations, whether describing the motion of planets, the behavior of particles, or the dynamics of waves, time is symmetric. This means that the equations work just as well if time flows backward as they do when time flows forward. A video of a pendulum swinging, for instance, looks natural whether played forward or in reverse. This time symmetry raises a profound question. If the fundamental laws of physics don't dictate a forward flow, why do we experience time in one direction? The answer lies in a concept from thermodynamics: entropy. Entropy is a measure of disorder or randomness in a system, and it is governed by the second law of thermodynamics, which states that in an isolated system, entropy tends to increase over time. In simple terms, things naturally progress from order to disorder. A pristine room becomes messy, a hot cup of coffee cools, and an ice cube melts in a warm drink. These processes are irreversible, and they define the arrow of time. This increase in entropy is why we remember the past but not the future. Consider a broken glass on the floor. Its scattered shards tell a story of what happened. The glass was whole, it fell, and it shattered. But you never see the reverse: a shattered glass spontaneously reassembling itself. This irreversibility, dictated by increasing entropy, gives us our sense of time moving forward. But why does entropy increase at all? The answer may lie in the conditions of the early universe. When the universe began with the Big Bang, it was in an extremely low entropy state, a state of remarkable order. Over billions of years, as stars formed, galaxies evolved, and energy dispersed, entropy steadily increased. Today, the universe is far more disordered than it was at its inception, and this ongoing increase in entropy sets the direction of the arrow of time. This connection between entropy and time has profound implications for our understanding of the cosmos. If the arrow of time is tied to the universe's expansion, what happens if the universe eventually contracts? Some cosmological models suggest that a contracting universe might reverse the arrow of time, causing entropy to decrease and events to unfold in reverse. In such a scenario, would we experience time backward, remembering the future instead of the past? Or would our perception remain unchanged, tied to the subjective experience of increasing entropy? The arrow of time also raises questions about the nature of time itself. Is time an illusion, a construct of our perception, or is it a fundamental property of the universe? Some physicists argue that the passage of time is not a universal truth, but a consequence of how we, as conscious beings, process information. Our brains organize experiences into a sequence, creating the illusion of a flowing river of time. In this view, past, present, and future all exist simultaneously in a block universe, where time is a dimension, like space, and the arrow of time is simply our way of navigating it. Yet, the subjective experience of time's flow remains one of the most profound aspects of human existence. We feel the relentless march of time, the inescapable pull toward the future, and the fleeting nature of the present. This emotional connection to time is deeply tied to our understanding of mortality, memory, and identity. Could this subjective experience be explained by entropy as well? Some researchers suggest that our brains, as highly ordered systems, are uniquely sensitive to entropy. The processes of memory formation and cognition may rely on the irreversible flow of time, linking our perception to the universe's thermodynamic arrow. Entropy and the arrow of time are not just abstract concepts. They have practical implications for the fate of the universe. As entropy continues to increase, the universe moves toward a state of maximum disorder, a scenario known as heat death. In this state, all energy is evenly distributed and no useful work can be done. Stars will burn out, galaxies will drift apart, and even black holes will evaporate, leaving a cold, dark, featureless cosmos. If this is the ultimate fate of the universe, what does it mean for the arrow of time? Will time cease to exist when entropy reaches its maximum, or will it continue to tick forward, even in a lifeless void? Despite the dominance of entropy in shaping the arrow of time, there are places in the universe where time seems to behave differently. In the quantum realm, particles can exhibit time reversal symmetry, where events appear identical whether played forward or backward. Similarly, in extreme environments like black holes or the early universe, the distinctions between past and future blur, challenging our conventional understanding of time. These anomalies suggest that the arrow of time may not be as universal as it seems. Perhaps it is a local phenomenon, emerging only under certain conditions? If so, could there be regions of the cosmos where time flows backward, or where multiple arrows of time coexist, pointing in different directions? And if we could enter such regions, what would happen to our perception of time? Would we adapt to the new arrow, or would we become untethered from our experience of reality? The arrow of time also intersects with the concept of time travel. If we could reverse the flow of entropy, could we turn back the clock and revisit the past? Some theories suggest that manipulating entropy could enable controlled time travel, though the energy requirements and practical challenges are staggering. Others argue that the very act of reversing entropy would violate the second law of thermodynamics, making backward time travel fundamentally impossible. As we grapple with these questions, the arrow of time remains one of the most profound mysteries of existence. It defines our lives, shapes our understanding of the universe, and challenges us to confront the nature of reality itself. Whether it is a fundamental property of the cosmos or a construct of our perception, the arrow of time reminds us that we are part of a vast, ever-changing universe, moving inexorably forward through the tapestry of space-time. Advanced civilizations and time manipulation. Throughout human history, the notion of advanced civilizations has captured our imagination. From alien species with technology far surpassing our own to humanity's distant descendants mastering the cosmos, the possibilities stretch beyond the limits of our current understanding. If time travel and manipulation are possible, it raises an extraordinary question. Could advanced civilizations, either elsewhere in the universe or in our future, have already unlocked the secrets of time? The idea that highly advanced beings might control time is not as far-fetched as it may seem. According to the Kardashev scale, a framework developed by astrophysicist Nikolai Kardashev, civilizations can be categorized by their ability to harness energy. A Type 1 civilization controls the energy of its home planet. A Type 2 civilization harnesses the energy of its star, and a Type 3 civilization wields the energy of its entire galaxy. The technological leaps required to reach these levels could potentially include the manipulation of time itself. Imagine a civilization capable of engineering closed time-like curves, CTCs, or stabilizing wormholes for interstellar travel. These advanced beings could traverse time as easily as we traverse continents, exploring not only distant stars but also their own past and future. The implications are staggering. Historical events might be studied firsthand, the mysteries of the universe unraveled by direct observation, and even the course of civilizations influenced by interventions from the future. But if such civilizations exist, where are they? The Fermi paradox, which questions why we haven't yet observed evidence of extraterrestrial life, becomes even more perplexing when considering time manipulation. Could these civilizations exist outside our timeline, observing us as we might study a fossilized insect in amber? If they possess the ability to navigate time, they might choose not to interfere with less advanced species, adhering to some form of temporal non-interference akin to the prime directive in science fiction. One fascinating possibility is that time manipulation could allow advanced civilizations to achieve practical immortality. By stepping outside the normal flow of time, they could avoid the natural decay of their environments or even their own biological or artificial forms. Such beings might exist in a state of temporal stasis, emerging only when conditions in the universe align with their objectives. Alternatively, they could operate on vastly different timescales, with their years spanning millennia from our perspective. If time travel enables the observation or alteration of historical events, it raises profound ethical questions. Would an advanced civilization intervene to prevent catastrophic events, such as asteroid impacts or mass extinctions? Or would they view these occurrences as natural parts of a timeline that must remain unaltered? The butterfly effect, where small changes in the past lead to massive alterations in the future, might deter even the most advanced beings from tampering with history. But what if time travel is already happening, and we simply don't recognize it? Some theorists speculate that anomalies in the historical record, unexplained technological leaps, sudden cultural shifts, or mysterious figures, could be evidence of time travelers. Legends of gods, angels, or otherworldly beings might, in some cases, be interpreted as encounters with individuals from advanced civilizations operating outside our timeline. However, these ideas remain speculative and controversial, lacking concrete evidence. One intriguing concept involves the idea of self-fulfilling time loops, where the actions of an advanced civilization are necessary to bring about its own existence. For instance, a future civilization might travel back in time to seed life on a barren planet, only to discover that they were, in fact, creating the conditions for their own emergence. Such loops challenge our understanding of causality and highlight the strange, almost paradoxical nature of time. Advanced civilizations might also manipulate time for strategic purposes. In warfare, the ability to slow down or speed up time relative to an enemy could provide an overwhelming advantage. A civilization that can effectively pause time might use the interval to advance its technology, consolidate resources, or outmaneuver its rivals. Such capabilities would make these beings almost godlike in their influence over the universe. Another compelling idea is that time manipulation could be used to explore alternate timelines or parallel universes. If the multiverse exists, advanced civilizations might develop technologies to navigate these dimensions, accessing countless versions of reality. This capability could allow them to choose the most favorable outcomes, effectively creating a form of temporal optimization. However, the ethical implications of selecting one timeline over another are profound, raising questions about the value of alternate realities and the consequences of abandoning them. The notion of advanced civilizations mastering time manipulation also invites speculation about humanity's future. If we survive long enough to become a Type 2 or Type 3 civilization, could we unlock the secrets of time travel? Some theorists argue that our first steps in this direction might involve mastering gravitational fields, as Einstein's theory of general relativity suggests that gravity and time are intrinsically linked. Technologies capable of manipulating gravity, perhaps through artificial black holes or advanced space-time engineering, could pave the way for time control. If humanity does achieve this level of advancement, it might radically transform our understanding of existence. Time could become a resource to be managed, a dimension to be navigated, or even a medium of communication. Future humans might send messages across time, guiding their ancestors to avoid catastrophic paths or achieve specific goals. This raises a tantalizing question. If future civilizations are already communicating with us, would we recognize their signals? Some scientists have proposed that anomalous phenomena, such as bursts of gamma rays or unexplained signals from space, might be attempts at communication from advanced civilizations using technologies beyond our understanding. If time manipulation is involved, these signals could originate from our own future or even from alternate timelines. Yet, the mastery of time comes with risks. The ability to alter or bypass the natural flow of time could destabilize the fabric of space-time itself, creating unforeseen consequences. Some physicists warn that time manipulation might lead to singularities, paradoxes, or even the collapse of causality. Advanced civilizations might approach time travel with extreme caution, fully aware of the dangers involved. Ultimately, the question of advanced civilizations and time manipulation reflects our own aspirations and fears. It challenges us to imagine a future where humanity transcends its limitations, achieving a level of understanding and control over the universe that seems almost magical. But it also reminds us of the responsibilities that come with such power. If time is a resource, it must be used wisely. If it is a dimension, it must be navigated carefully. And if it is a mystery, it must be respected. As we continue to search the cosmos for signs of advanced civilizations, we are also searching for reflections of our potential future. Could we one day join the ranks of those who have mastered time, or are we destined to remain bound by its relentless flow? Perhaps the answers lie not in distant galaxies, but within the fabric of time itself, waiting to be uncovered by those brave enough to ask the right questions. Time travel in popular culture. Time travel, more than any other concept in science fiction, captures our collective imagination with its boundless possibilities. It invites us to ponder the what-ifs of existence, offering a way to explore the past, reshape the present, and glimpse the future. Across literature, film, television, and art, time travel has become a narrative tool, not only to entertain, but also to reflect on the human condition. Popular culture, in turn, shapes our understanding of time travel, intertwining science with storytelling. The roots of time travel in popular culture can be traced back to H.G. Wells' The Time Machine, 1895, the seminal novel that introduced the concept of a device capable of traversing time. Wells' story was not merely a technical exploration of time travel, but a profound commentary on societal evolution, class struggle, and the inexorable march of entropy. The time traveler's journey to the distant future revealed a decayed Earth populated by the Eloi and Morlocks, a vision of human destiny shaped by technological and social stagnation. This novel laid the groundwork for how time travel would be used in fiction, as a mirror reflecting humanity's fears, hopes, and possibilities. From Wells' Victorian England, time travel expanded into a global phenomenon, particularly with the advent of cinema. Films brought time travel to life with visual splendor and dramatic storytelling. In the mid-20th century, movies like The Time Travelers, 1964, and Time After Time, 1979, explored the mechanics and consequences of temporal journeys. However, it was the 1980s that catapulted time travel into mainstream cultural consciousness with the blockbuster hit Back to the Future, 1985. This film blended humor, adventure, and an engaging exploration of causality as Marty McFly accidentally alters his parents' past and struggles to restore the timeline. The DeLorean time machine, powered by the enigmatic flux capacitor, became an enduring symbol of pop culture's fascination with time travel. Television also embraced time travel, transforming it into an episodic vehicle for storytelling. Doctor Who, a British science fiction series that began in 1963, has become one of the longest-running and most iconic depictions of time travel in popular culture. The Doctor's TARDIS, a ship capable of traveling anywhere in space and time, provides the backdrop for countless adventures exploring historical moments, alien worlds, and philosophical dilemmas. The show's emphasis on the moral and ethical implications of time travel has resonated with generations of viewers. American television series like Quantum Leap, 1989 to 1993, offered a different perspective, focusing on personal redemption and human connection. In the show, Dr. Sam Beckett leaps into the bodies of people across different times, tasked with putting right what once went wrong. Each leap explores issues of identity, justice, and the ripple effects of small changes in history. The concept of time travel as a means of correcting mistakes became a recurring theme in popular culture, reflecting humanity's enduring desire to rewrite its past. As the 21st century began, time travel narratives grew increasingly complex, reflecting advances in science and technology, as well as shifting cultural anxieties. Films like Looper, 2012, and Primer, 2004, brought gritty, cerebral takes on time travel, emphasizing paradoxes, ethics, and the psychological toll of manipulating time. Meanwhile, blockbusters like Avengers, Endgame, 2019, and Christopher Nolan's Tenet, 2020, redefined time travel as both a narrative device and a spectacle, blending intricate plots with cutting-edge visual effects. These films challenge audiences to grapple with the mechanics of time travel while delivering high-stakes drama and action. Beyond entertainment, time travel in popular culture often serves as a philosophical exploration of humanity's relationship with time itself. Stories like The Butterfly Effect, 2004, and Donnie Darko, 2001, delve into the fragility of causality, suggesting that even the smallest actions can have profound and unpredictable consequences. Similarly, series like Dark, 2017 to 2020, a German science fiction drama, weave intricate timelines and interconnected fates, questioning whether free will can truly exist in a deterministic universe. One of the most compelling aspects of time travel in popular culture is its ability to address universal themes. It allows creators to explore regret and nostalgia, as characters revisit their past to heal old wounds or rekindle lost relationships. Films like About Time, 2013, and The Time Traveler's Wife, 2009, use time travel as a metaphor for love, memory, and the fleeting nature of life. These narratives resonate deeply with audiences because they speak to our shared longing to hold on to precious moments and make the most of the time we have. Time travel also serves as a lens for examining societal issues. In Octavia Butler's Kindred, 1979, the protagonist is repeatedly transported to the antebellum South, confronting the horrors of slavery and the intergenerational impact of systemic oppression. By juxtaposing contemporary perspectives with historical realities, Butler uses time travel to challenge readers' assumptions and spark critical conversations about history and identity. In addition to exploring the past, time travel narratives often grapple with the uncertainty of the future. Dystopian tales like The Terminator, 1984, and 12 Monkeys, 1995, envision futures shaped by humanity's mistakes, with time travel as the only hope for redemption. These stories reflect cultural anxieties about technology, war, and environmental collapse, urging audiences to consider the long-term consequences of their actions. Popular culture's portrayal of time travel has also influenced real-world scientific exploration. Scientists like Kip Thorne, who served as a consultant for the film Interstellar, have used time travel stories as a springboard for theoretical research. The depiction of a black hole's event horizon in the film, for instance, was based on cutting-edge physics and inspired further studies into gravitational time dilation. This interplay between fiction and science demonstrates how imagination and creativity can drive innovation and deepen our understanding of the universe. Yet, time travel in popular culture is not without its limitations. Many narratives simplify or ignore the complexities of physics, focusing instead on emotional or dramatic stakes. While this can make stories more accessible, it often leads to misconceptions about the scientific plausibility of time travel. For example, the depiction of paradoxes, while engaging, is rarely grounded in current scientific theories, which often suggest that the universe may inherently prevent such contradictions. Despite these challenges, the enduring appeal of time travel in popular culture lies in its ability to bridge the gap between science and storytelling. It invites audiences to dream of a reality where the constraints of time are lifted, offering hope, wonder, and reflection. As science advances and our understanding of time deepens, the stories we tell about time travel will continue to evolve, inspiring new generations to imagine the impossible. Ultimately, time travel in popular culture is not just about bending space-time or solving paradoxes. It's about exploring what it means to be human. Through tales of adventure, love, loss, and discovery, time travel connects us to our past, present, and future, reminding us that time is not just a dimension to be measured but an experience to be lived. Experimental evidence for time dilation. Time dilation, one of the most fascinating consequences of Einstein's theory of relativity, is not just a theoretical concept. It's a scientifically observed and experimentally verified phenomenon. The idea that time flows at different rates depending on speed and gravity has been tested and confirmed in numerous experiments, offering tangible evidence of the flexible nature of time. These experiments not only deepen our understanding of the universe, but also provide a foundation for exploring the possibility of time travel. To grasp the significance of time dilation, it's essential to revisit its two main forms: velocity-based time dilation, described by Einstein's special theory of relativity, and gravitational time dilation, predicted by his general theory of relativity. Velocity-based time dilation: the faster you move, the slower you age. The first form of time dilation occurs when an object approaches the speed of light. Einstein's special relativity tells us that as an object's velocity increases, time for that object slows down relative to an observer at rest. This effect has been confirmed through a series of groundbreaking experiments. One of the earliest and most famous confirmations came from muon decay experiments. Muons are subatomic particles created when cosmic rays interact with Earth's atmosphere. These particles have a very short lifespan, on average just 2.2 microseconds before they decay. However, muons traveling at near light speeds were observed to persist much longer than expected when detected at the Earth's surface. The explanation? Time dilation. For the fast-moving muons, time flows more slowly compared to an observer on Earth, allowing them to live longer and travel further than they otherwise would. The principles of velocity-based time dilation have also been tested with precision using atomic clocks. In 1971, physicists Haffel and Keating conducted an experiment involving highly accurate cesium atomic clocks. They placed synchronized clocks on commercial jet planes and flew them around the Earth, both eastward and westward. Upon their return, the airborne clock showed measurable differences compared to a stationary clock on the ground. The results matched the predictions of special and general relativity. Time had passed more slowly for the clocks on the planes due to their high speeds. Gravitational time dilation. The stronger the gravity, the slower time flows. The second form of time dilation is caused by gravity. According to Einstein's general relativity, massive objects warp spacetime, creating a gravitational field that slows time for objects within it. The closer an object is to the source of gravity, the slower time moves relative to an observer farther away. This effect was first demonstrated in 1960 by physicist Robert Vesset and his team using a highly sensitive instrument called a hydrogen maser clock. By placing one clock on the ground and another in a high-altitude aircraft, they measured the difference in the passage of time. As predicted, the clock closer to the Earth's surface, where gravity is stronger, ticked more slowly than the one at higher altitude. Gravitational time dilation has also been confirmed with extreme precision through experiments involving satellites. The Global Positioning System, GPS, provides one of the most practical examples of this phenomenon. GPS satellites orbit the Earth at an altitude of approximately 20,000 kilometers, where the gravitational pull is weaker than on the planet's surface. As a result, time on these satellites runs slightly faster than on the ground. If this difference were not accounted for, GPS systems would experience errors of several kilometers per day, rendering them useless for navigation. To correct this, engineers use Einstein's equations to adjust the satellite's clocks, ensuring accurate positioning for billions of devices worldwide. The twin paradox, a thought experiment brought to life. The concept of time dilation is often illustrated through the twin paradox, a thought experiment that has become a hallmark of relativity discussions. Imagine one twin traveling through space at near light speed while the other remains on Earth. Upon the traveling twins' return, they find that they have aged much less than their sibling, who experienced time at a normal rate. While the twin paradox may seem purely hypothetical, experiments with high-speed particles and atomic clocks confirm that time dilation is a real, measurable effect. In the 1970s, researchers conducted experiments with high-speed particles and particle accelerators, effectively simulating the twin paradox. Particles moving at relativistic speeds experience significantly slower internal clocks compared to particles at rest. These results align perfectly with the predictions of special relativity and demonstrate that time dilation is not confined to theoretical models. It is an observable feature of our universe. Gravitational time dilation in extreme environments. One of the most dramatic confirmations of gravitational time dilation came from the study of pulsars, dense, rapidly rotating remnants of supernova explosions. These cosmic beacons emit beams of electromagnetic radiation at regular intervals, acting like incredibly precise cosmic clocks. When pulsars are observed in binary systems, where they orbit a massive companion star, the timing of their signals exhibits subtle shifts. These shifts are caused by the intense gravitational fields in the system, which slow down time for the pulsar relative to Earth. By studying these effects, astronomers have tested and verified the predictions of general relativity with remarkable accuracy. Perhaps the most famous depiction of gravitational time dilation in popular culture is the film Interstellar. In the movie, astronauts visiting a planet near a supermassive black hole experience severe time dilation. Hours for them correspond to years for those farther from the black hole. While dramatized for cinematic effect, the underlying science is rooted in real physics. Black holes, with their immense gravitational pull, represent the most extreme environments for time dilation. Near their event horizons, time slows to such an extent that it appears to stop altogether for an outside observer. Time dilation and its implications for time travel. The experimental evidence for time dilation confirms that time is not an absolute constant, but a flexible dimension influenced by speed and gravity. This opens the door to practical forms of one-way time travel into the future. For instance, a spacecraft traveling at near-light speed would allow its passengers to leap forward in time relative to those remaining on Earth. Similarly, Orbiting near a black hole or another massive object could enable an astronaut to experience significant time dilation, effectively skipping forward into the future. However, traveling backward in time remains a more elusive challenge. While the laws of relativity permit the bending of space-time, creating the conditions for backward time travel requires exotic phenomena such as wormholes or closed time-like curves. These remain speculative, with no experimental evidence to support their existence. A universe defined by time's elasticity. The experimental verification of time dilation has revolutionized our understanding of time and space. It demonstrates that time is not a rigid, universal constant, but a dynamic feature of the cosmos, shaped by velocity and gravity. These discoveries bridge the gap between abstract theory and observable reality, paving the way for future exploration of time manipulation. As we continue to probe the mysteries of time, the experiments confirming time dilation remind us of the universe's profound complexity. They offer a glimpse into a reality where time is not merely a measure of moments, but a dimension as fluid and intricate as space itself. Could we be time travelers? The idea that humans might already be time travelers is as provocative as it is mysterious. Could we, in some way, already be traversing the fabric of time without realizing it? This question doesn't just spring from the realms of science fiction, but from the curious intersection of modern physics, ancient myths, and speculative theories about the nature of existence. To explore this, we must consider the possibility of unconscious time travel, the influence of future beings on the present, and whether humanity itself might one day return to its own past. Time travel in the here and now. In a sense, we are all time travelers, but in the most basic way. We are constantly moving forward through time at a rate of 1 second per second. This journey, dictated by the laws of entropy and the arrow of time, is so fundamental to our existence that we rarely question it. But what if there are ways to alter our temporal velocity, to speed up or slow down our passage through time? Experiments with time dilation, as discussed earlier, demonstrate that moving faster or being near a strong gravitational field can distort time's flow. Astronauts aboard the International Space Station, for example, age very slightly slower than people on Earth due to the effects of both velocity and gravity. Yet, these small-scale distortions raise an intriguing thought. Could there be more profound instances of temporal anomalies that affect humans unknowingly? Reports of déjà vu, premonitions, or feelings of lost time have often been interpreted through the lens of time travel. While these phenomena are typically explained as quirks of memory or perception, some theorists have suggested they might hint at subtle shifts in the flow of time. Could the human brain, a complex network of electrical impulses and quantum effects, occasionally tap into alternate timelines or future events? Ancient myths and temporal beings. Human fascination with time travel is not new. It has roots in ancient myths and folklore. Many cultures tell stories of individuals who seemingly transcended time. In Hindu mythology, for instance, the Mahabharata describes King Revata, who traveled to meet the creator god Brahma. When he returned to Earth, he found that ages had passed, and his world had changed beyond recognition. Similarly, tales of Rip Van Winkle-like figures, who sleep for decades only to awaken in a transformed society, appear in diverse traditions. These myths often parallel the effects of time dilation or temporal displacement, leading some to speculate whether they might be inspired by real phenomena. If humanity has unknowingly encountered natural time loops or anomalies, perhaps caused by black holes, wormholes, or other cosmic events, such experiences might have been interpreted as divine or supernatural interventions. These stories, passed down through generations, could represent early attempts to grapple with the mysteries of time. Future humans visiting the past. One of the most compelling questions about time travel is whether humanity itself might someday master the technology to travel backward in time. If this were possible, future humans could already be among us, subtly influencing the course of history. This idea has inspired countless theories, from ancient astronauts shaping early civilizations to time travelers steering humanity away from disaster. The future humans hypothesis is not as far-fetched as it may sound. If humanity survives long enough to become a Type 2 or Type 3 civilization on the Kardashev scale, we may develop the ability to manipulate space-time. Advanced technology might allow us to create stable wormholes, engineer closed time-like curves, or even simulate entire timelines. These achievements, while distant, are not ruled out by the known laws of physics. If future humans were visiting the past, how might we recognize them? Some theorists point to historical anomalies as potential evidence. For instance, certain technological advances or artistic depictions, like the infamous ancient astronaut carvings, have been interpreted as hints of temporal interference. While these claims are controversial and often speculative, they highlight the enduring allure of time travel in shaping our view of history. The Fermi paradox and time travelers. The absence of evidence for extraterrestrial civilizations, known as the Fermi paradox, might also be explained through the lens of time travel. If advanced civilizations have achieved the ability to navigate time, they may exist outside our observable timeline. This could mean that the universe is teeming with life, but much of it exists in different temporal states, inaccessible to us in the present. Alternatively, advanced civilizations might adopt a policy of non-interference, avoiding actions that could disrupt the timeline or reveal their presence. This concept, akin to the prime directive in science fiction, suggests that time travelers might observe us silently, ensuring that their actions do not create paradoxes or alter history in unintended ways. Could we be the time travelers? Another intriguing possibility is that humanity's entire existence might be the result of time travel. Some scientists and philosophers have proposed that the universe itself could be a self-contained time loop, where the actions of advanced beings in the distant future create the conditions for their own past. For instance, future humans might seed the early Earth with life, or influence the development of technology to ensure their eventual existence. This notion ties into the idea of the anthropic principle, which suggests that the universe's physical constants are fine-tuned to allow for life. If time travel is involved, the fine-tuning might not be coincidental, but the result of deliberate action by future beings ensuring their own creation. Time slips and unexplained phenomena. Reports of time slips add another layer to the mystery. These are instances where individuals claim to experience sudden, inexplicable shifts in time, such as finding themselves in a different era or observing events from the past. While most accounts are anecdotal and lack scientific verification, they raise intriguing questions about the nature of time and consciousness. Could natural phenomena, such as gravitational anomalies or fluctuations in space-time, create localized time distortions? Some researchers have speculated that certain geographic regions, such as the Bermuda Triangle, might exhibit unusual temporal properties. While evidence for such claims remains elusive, the possibility of natural time anomalies cannot be entirely dismissed. The quantum mind hypothesis. Another avenue for exploring unconscious time travel lies in the field of quantum biology. Some scientists propose that the human brain might exhibit quantum properties, allowing it to interact with time in unconventional ways. If consciousness operates at the quantum level, it might enable fleeting glimpses of future events or alternate timelines. This idea is speculative but fascinating, as it suggests that time travel might not require advanced machines or exotic matter. Instead, the key to understanding time could lie within ourselves, hidden in the intricate workings of the brain. A future beyond time. Ultimately, the question of whether we are already time travelers reflects our deep curiosity about our place in the universe. While there is no concrete evidence that humanity has traversed time beyond the forward flow dictated by entropy, the possibility remains an open frontier for science and philosophy. As we continue to explore the mysteries of time, we may discover that our journey through it is far more complex and far more wondrous than we ever imagined. Wormholes as cosmic doorways. Imagine a gateway that could take you to the farthest reaches of the universe, or even to a different moment in time. An enigmatic portal bridging the unfathomable distances of space and the elusive depths of time. Wormholes, theoretical constructs rooted in Einstein's general theory of relativity, have long captivated the imagination of scientists and dreamers alike. These cosmic doorways could hold the key to exploring not just distant galaxies, but also alternate eras, offering tantalizing possibilities for time travel. To understand the allure of wormholes, we must first revisit the concept of space-time as a malleable fabric. Einstein's equations reveal that gravity arises from the curvature of this fabric, shaped by the presence of mass and energy. Wormholes, also known as Einstein-Rosen bridges, represent a more radical bending of this fabric, shortcuts connecting two disparate regions of space-time. Imagine a piece of paper with two dots representing points A and B. Folding the paper so the dots touch creates a shortcut between them, bypassing the need to traverse the paper's surface. This is the essence of a wormhole. The structure of a wormhole. A wormhole consists of two mouths and a throat connecting them. Each mouth represents an entrance or exit, while the throat is the passageway through space-time. Theoretically, a wormhole could link points separated by vast distances or even different times. The idea was first proposed by Albert Einstein and Nathan Rosen in 1935, though their initial interpretation treated wormholes as untraversable. Later refinements by physicists like Kip Thorne and John Archibald Wheeler explored the possibility of traversable wormholes, which could theoretically allow matter and information to pass through. For a wormhole to remain open long enough for travel, it would need to be stabilized against collapse. Here lies one of the most significant challenges. The intense gravitational forces within a wormhole would naturally cause it to collapse almost instantly. To counteract this, physicists have proposed the use of exotic matter, a theoretical form of matter with negative energy density. Unlike ordinary matter, exotic matter exerts a repulsive gravitational force, potentially keeping the wormhole's throat open. While exotic matter has yet to be observed directly, phenomena like the Casimir effect, which involves negative energy between two closely spaced plates, hint at its theoretical viability. Wormholes and time travel. Wormholes are not just portals through space. They could also serve as gateways through time. If one mouth of a wormhole were exposed to intense gravitational time dilation, such as by placing it near a black hole, or moved at near-light speeds, the two mouths could become desynchronized in time. This time difference would effectively turn the wormhole into a time machine, allowing travelers to step into one mouth and emerge at a different era. Theoretical physicist Kip Thorne popularized this idea in the 1980s, inspiring not only scientific inquiry, but also the imaginations of writers and filmmakers. However, the concept of using wormholes for time travel raises significant questions about causality. For instance, what would prevent someone from traveling back in time and creating a paradox, such as the infamous grandfather paradox? While some theories, like the Novikov self-consistency principle, suggest that paradoxes might resolve themselves naturally, the idea of altering history remains one of the most contentious aspects of time travel through wormholes. Detecting wormholes in the cosmos. If wormholes exist, could we find evidence of them in the universe? Some scientists suggest that wormholes might leave detectable signatures, such as unusual gravitational lensing effects. Gravitational lensing occurs when massive objects bend light from distant stars, creating arcs or distorted images. A wormhole could produce a unique lensing pattern, differing from that caused by black holes or galaxies. Astronomers using telescopes like the Hubble Space Telescope or the upcoming James Webb Space Telescope may one day identify these patterns, providing indirect evidence of wormholes. Another possible clue lies in the behavior of particles and radiation. If a wormhole connects two regions of space, particles or energy passing through it might leave anomalous traces detectable by advanced instruments. For instance, high-energy cosmic rays or bursts of gamma radiation could originate from wormhole interactions, offering tantalizing hints of their existence. Are wormholes natural or engineered? The origin of wormholes is another profound mystery. Could they form naturally in the chaotic interplay of cosmic forces? Or might they be the creations of advanced civilizations? Natural wormholes, if they exist, could arise from the quantum fluctuations that permeate space-time, manifesting briefly at microscopic scales. However, stabilizing and enlarging such wormholes for practical use would require technologies far beyond our current capabilities. Alternatively, wormholes might be artificially engineered. A sufficiently advanced civilization, capable of manipulating space-time on a grand scale, could construct and stabilize wormholes as tools for exploration, transportation, or communication. If this is the case, such civilizations might use wormholes to traverse the vast distances of the universe, effectively bypassing the constraints of light-speed travel. Wormholes in popular culture. The concept of wormholes has transcended scientific theory to become a staple of science fiction. From Carl Sagan's Contact, where wormholes facilitate communication with alien civilizations, to Christopher Nolan's Interstellar, where a wormhole near Saturn enables humanity's survival, these cosmic doorways serve as powerful symbols of exploration and discovery. While fictional depictions often simplify or dramatize the science, they inspire audiences to ponder the profound possibilities of wormholes as both a scientific reality and a narrative device. Challenges and limitations. Despite their allure, wormholes face significant scientific and practical hurdles. Stabilizing a wormhole requires exotic matter, which remains hypothetical. Even if exotic matter exists, the energy demands to stabilize and maintain a wormhole would be astronomical. Additionally, the intense gravitational forces within a wormhole could create severe tidal effects, potentially destroying any object attempting to pass through. There is also the question of wormhole stability over time. Even if a wormhole could be stabilized temporarily, it might still collapse due to quantum effects or interactions with matter and energy. Preventing such collapse would require a deep understanding of quantum gravity, a field that remains largely unexplored. The promise of wormholes. Wormholes, if they exist, represent the ultimate expression of humanity's desire to transcend limitations, be they spatial, temporal, or technological. They challenge us to imagine a universe where distances and time are no longer barriers, where the boundaries of the possible are continually expanded. Whether as tools for interstellar travel or as gateways to the past and future, wormholes embody the dream of unlocking the universe's deepest secrets. As we continue to study the cosmos and develop our understanding of space-time, the possibility of discovering or creating wormholes remains one of the most exciting frontiers in science. Could these cosmic doorways one day become a reality? And if so, what lies on the other side of the threshold? Energy requirements for time travel. Time travel, whether through wormholes, closed time-like curves, or other theoretical methods, is not only a challenge of physics but also one of immense energy demands. Manipulating the very fabric of space-time to bend it to our will requires a level of energy that seems almost incomprehensible. To understand the practicality of time travel, we must delve into the staggering energy requirements and the potential sources that could make it possible or highlight its limitations. The energy of warping space-time. At the core of any time travel mechanism is the manipulation of space-time itself. Einstein's equations of general relativity show that mass and energy curve space-time, creating the gravitational fields we experience. To create a structure like a wormhole or a closed time-like curve, we would need to generate gravitational distortions far greater than those found naturally in the universe, such as those around black holes or neutron stars. Let's take wormholes as an example. A traversable wormhole, one that allows for safe passage, would require exotic matter to counteract the intense gravitational forces trying to collapse it. Exotic matter, with its negative energy density, has only been theorized and might require advanced quantum effects to produce. The amount of exotic matter needed would depend on the size of the wormhole, but even for a small wormhole, the energy demands would likely exceed the output of all the stars in our galaxy combined. Creating a wormhole throat large enough for human or spacecraft travel would also require enormous amounts of conventional energy. A rough calculation suggests that the energy required to stabilize a small wormhole could approach the Planck energy, the theoretical maximum energy scale in the universe, far beyond what any known technology can achieve. The Alcubierre warp drive, a case study in energy. The Alcubierre drive, a theoretical model for faster-than-light travel, provides insight into the energy challenges of space-time manipulation. Proposed by physicist Miguel Alcubierre in 1994, this concept involves creating a warp bubble around a spacecraft, compressing space-time in front of it, and expanding it behind. While not strictly a time machine, the drive demonstrates how manipulating space-time could enable travel to distant points, and potentially into the past or future. The energy requirements for an Alcubierre drive are staggering. Early estimates suggested it would require the energy equivalent of several stars, though refinements to the model have reduced the estimate to the mass energy of a large planet. Even this reduced requirement remains unattainable with current technology. Moreover, the drive would also require exotic matter to stabilize the warp bubble, introducing another layer of complexity. Black holes as energy sources. Black holes, with their immense gravitational fields, naturally warp space-time and create extreme time dilation. Harnessing the energy of a black hole could theoretically provide the power needed for time travel. One proposed method involves using a Kerr black hole, a rotating black hole that might harbor a ring-shaped singularity. Such singularities could allow for closed time-like curves, enabling time travel under certain conditions. However, tapping into the energy of a black hole presents monumental challenges. Even if we could approach a black hole safely, extracting its energy would require advanced technologies capable of withstanding immense gravitational forces and radiation. One speculative method is the Penrose process, where matter is thrown into a black hole's ergosphere, the region just outside its event horizon, to extract rotational energy. While the Penrose process is theoretically efficient, implementing it on the scale needed for time travel would require engineering feats far beyond our current capabilities. Quantum mechanics and energy fluctuations. Quantum mechanics offers another avenue for exploring the energy needs of time travel. At the quantum scale, energy fluctuations in empty space, known as vacuum energy, could provide a source of negative energy needed for exotic matter. The Casimir effect, where two closely spaced plates create a region of negative energy density, demonstrates that quantum effects can produce small amounts of exotic energy. Scaling quantum effects to macroscopic levels, however, presents significant obstacles. The energy densities involved in quantum fluctuations are tiny, and amplifying them to the level needed for stabilizing wormholes or creating time machines would require breakthroughs in both quantum field theory and engineering. Nevertheless, some theorists argue that harnessing vacuum energy might one day unlock new possibilities for time travel. Cosmic strings, natural energy pathways. Cosmic strings, hypothetical one-dimensional defects in space-time formed during the early universe, could provide another potential mechanism for time travel. These ultradense structures, if they exist, would create immense gravitational fields capable of bending space-time. Intersecting or looping cosmic strings might generate closed time-like curves, allowing for travel to the past. The energy involved in manipulating or even locating cosmic strings would be immense. Their theoretical energy density is so high that a single cosmic string could warp space-time over astronomical distances. To use cosmic strings for time travel, we would need to find or create them, a feat requiring energy levels rivaling those of the Big Bang itself. Antimatter, a potential energy source. Antimatter, often portrayed in science fiction as a power source for futuristic technologies, is another potential candidate for time travel energy requirements. When antimatter and matter annihilate, they release energy with near-perfect efficiency, making antimatter one of the most energy-dense substances in the universe. However, producing and storing antimatter poses enormous challenges. Current methods, such as using particle accelerators, produce antimatter in microscopic quantities at enormous energy costs. Scaling up antimatter production to meet the demands of time travel would require technological breakthroughs in containment and energy efficiency. The Kardashev scale and energy mastery. Achieving the energy requirements for time travel may be feasible only for civilizations that have reached advanced stages of development on the Kardashev scale. A Type 1 civilization, which harnesses all the energy available on its home planet, might begin to experiment with small-scale time manipulation. A Type 2 civilization, capable of capturing the energy of its star, might develop technologies for creating and stabilizing wormholes. A Type 3 civilization, controlling the energy output of an entire galaxy, could potentially use these resources to master time travel. Humanity, currently at approximately 0.7 on the Kardashev scale, has a long way to go before reaching the energy levels required for time travel. Advancements in energy harvesting, fusion power, and quantum technologies may bring us closer, but the road ahead is steep. Ethical considerations of energy use. Even if we could access the energy needed for time travel, questions about its ethical implications remain. Diverting such vast amounts of energy for time travel could have significant consequences for the environment, society, and other scientific pursuits. Would the benefits of time travel justify the costs, or would such technology be better reserved for more immediate challenges, like combating climate change or ensuring global sustainability? A path toward the future. The energy requirements for time travel highlight the immense challenges involved in bending space-time to our will. Yet, they also serve as a testament to humanity's ingenuity and determination. While current technologies fall far short of the demands for time travel, continued advancements in physics and engineering may one day bring us closer to realizing this extraordinary dream. As we strive to unlock the secrets of the universe, the question of energy remains central. Can we find ways to harness the power of the cosmos? Or will the barriers of energy forever keep time travel just out of reach? The answer may lie in the stars, or in the untapped potential of human imagination. The multiverse hypothesis. The concept of the multiverse, the idea that our universe is just one of countless others, has revolutionized how we think about reality, time, and existence itself. If the multiverse exists, it could solve some of the most perplexing paradoxes associated with time travel, and even provide a framework for exploring alternate timelines. The multiverse hypothesis extends beyond science fiction, touching on cutting-edge theories in quantum mechanics, cosmology, and string theory. Could this vast web of universes hold the key to unlocking the mysteries of time travel? What is the multiverse? The multiverse hypothesis suggests that our universe, with its stars, galaxies, and fundamental laws of physics, is not unique. Instead, it is part of a much larger system comprising numerous, potentially infinite, universes. Each universe within the multiverse may have its own distinct properties, including different physical constants, dimensions, and even alternate versions of history. Several scientific theories support the idea of a multiverse. 1. Quantum mechanics and many-worlds interpretation. In 1957, physicist Hugh Everett proposed the many-worlds interpretation of quantum mechanics. According to this theory, every quantum event creates a branching timeline, resulting in a new universe for each possible outcome. For instance, if you flip a coin, one universe forms where the result is heads, and another where it is tails. These branches are thought to exist simultaneously, representing a vast multiverse of parallel realities. 2. Cosmic inflation. The theory of eternal inflation, developed by physicist Alan Guth, suggests that the rapid expansion of the universe immediately after the Big Bang might have created pockets of space-time that evolved into separate universes. Each of these universes could have unique properties and physical laws. 3. String theory and extra dimensions. String theory, a candidate for unifying quantum mechanics and general relativity, posits the existence of multiple dimensions beyond the familiar three of space and one of time. Some versions of string theory imply the existence of a multiverse, where each universe occupies a different dimensional brane within a higher dimensional space. 4. Black holes as gateways. Some theories propose that black holes might create new universes within their singularities. If true, every black hole could be a gateway to an entirely new cosmos, each with its own unique properties. Time travel and the multiverse. The multiverse hypothesis offers an elegant solution to the paradoxes of time travel, such as the grandfather paradox. In a multiverse, traveling to the past would not alter your original timeline. Instead, it would create or connect you to an alternate timeline. For instance, if you traveled back and prevented your grandparents from meeting, you would not erase yourself from existence. Instead, you would create a new branch of reality where you were never born, leaving your original timeline unaffected. This concept aligns with the many-worlds interpretation, where every action spawns new universes. Time travelers, rather than disrupting their own pasts, might simply navigate between parallel realities. This would allow for free exploration of history without fear of paradoxes, as each change would be confined to its own distinct timeline. Navigating the multiverse. If the multiverse exists, how might one navigate between universes? Theoretical physics offers some speculative mechanisms. 1. Quantum tunneling. At the quantum level, particles can tunnel through energy barriers, appearing in places they seemingly shouldn't be able to reach. Some physicists speculate that quantum tunneling could extend to macroscale objects, potentially allowing for transitions between parallel universes. 2. Wormholes. Wormholes, as discussed earlier, are theoretical shortcuts through space-time. In a multiverse context, a wormhole might connect not just distant points in our universe, but entirely separate universes. Traversing such a wormhole could allow time travelers to access alternate realities. 3. Brain intersections. In string theory, universes are thought to exist on separate branes, higher dimensional surfaces within a vast bulk space. If two brains were to collide or intersect, it might create a temporary bridge between universes, offering a way to travel between them. 4. Advanced technology. An advanced civilization might develop technologies capable of manipulating the fabric of space-time to access parallel realities. For example, they might use energy from black holes or exotic matter to stabilize interuniversal gateways. Evidence for the multiverse. While the multiverse remains a theoretical construct, several lines of inquiry hint at its potential existence. 1. Cosmic microwave background, CMB, anomalies. The CMB, the afterglow of the Big Bang, contains subtle patterns that might indicate interactions between our universe and others. Some researchers have identified cold spots in the CMB that could be evidence of collisions with parallel universes. 2. Quantum entanglement. The phenomenon of entanglement, where particles remain connected regardless of distance, raises questions about the underlying nature of reality. Some interpretations suggest that entanglement might involve connections across multiple universes. 3. Mathematical necessity. Certain mathematical models in cosmology and string theory naturally imply the existence of a multiverse. These models are consistent with observed phenomena, lending indirect support to the hypothesis. Philosophical implications of the multiverse. The multiverse challenges our understanding of reality and identity. If parallel universes exist, what does it mean to be you? In one universe, you might be reading this text, while in another, you might be leading a vastly different life or not exist at all. This raises profound questions about free will, determinism, and the nature of consciousness. The multiverse also reshapes our understanding of time. If every possible version of history exists somewhere in the multiverse, then time travel might not involve altering the past, but merely shifting perspectives to another version of events. This view suggests that the past, present, and future are not fixed but part of a vast, interconnected web of possibilities. The multiverse in popular culture. The multiverse has become a popular theme in science fiction, inspiring stories that explore alternate histories, parallel lives, and the ethical dilemmas of time travel. Films like Doctor Strange and the Multiverse of Madness, series like Rick and Morty, and novels like Philip K. Dick's The Man in the High Castle illustrate the narrative richness of the multiverse concept. These stories often grapple with questions of identity, morality, and the consequences of exploring alternate realities. The challenges of proving the multiverse. Despite its theoretical appeal, proving the multiverse remains a formidable challenge. Directly observing other universes may be impossible, as they are likely separated from us by barriers beyond our technological reach. Even if evidence of interactions, such as CMB anomalies, is found, it may not be definitive proof. However, the absence of direct evidence does not invalidate the hypothesis. The multiverse may simply lie beyond the current limits of our observation and understanding, much like the existence of galaxies was once inconceivable before the invention of telescopes. The multiverse as a framework for time travel. The multiverse provides a compelling framework for reconciling the paradoxes and possibilities of time travel. By envisioning time as a branching tree rather than a linear arrow, it allows for exploration without contradiction, where every action and choice creates a new pathway through the cosmos. As humanity continues to probe the nature of the universe, the multiverse hypothesis reminds us that reality may be far richer and more complex than we ever imagined. Whether through the lens of science or imagination, the multiverse invites us to embrace the infinite and to consider what lies beyond the boundaries of our world and our time. Are wormholes stable? Wormholes, those fantastically mysterious, profoundly hypothetical tunnels through the vibrant fabric of space-time, ignite our imagination with visions of effortless interstellar travel and daring journeys through time. Yet, beneath their awe-inspiring theoretical allure lies a troubling and often perplexing question. Are they stable? Can these cosmic shortcuts withstand the intense forces that threaten to collapse them before we could even glimpse their dazzling interiors? Stability, as it turns out, is both the most thrilling and the most challenging hurdle in realizing the potential of wormholes. The fragility of wormholes. At their heart, wormholes are incredibly delicate structures, existing precariously within the tightly balanced equations of Einstein's general relativity. These equations, magnificent and intricate, describe how mass and energy warp the very essence of space-time, creating the gravitational fields we observe. A wormhole, rather than a simple curve in this cosmic fabric, is an audacious folding, a bold connection between distant or even disparate regions of space-time. However, this folding isn't free of its dangers. Left to the relentless grip of gravity, a wormhole's throat would almost immediately collapse, snapping shut faster than light itself could traverse it. The forces at play are incomprehensibly immense, turning the wormhole into an unnavigable trap. To prevent such catastrophic closure, we must stabilize these cosmic passageways. But the method for achieving this remains as elusive as it is tantalizing. Exotic matter, the cosmic glue. The key to stabilizing a wormhole, as proposed by brilliant physicists like Kip Thorne, lies in the use of exotic matter, a hypothetical form of matter with bizarre and fantastical properties. Exotic matter isn't like the ordinary, reassuringly familiar matter that forms stars, planets, or people. It has negative energy density, meaning it exerts a repulsive gravitational force instead of the comforting, familiar pull we experience on Earth. This repulsion could counteract the overwhelming inward pull of gravity at the wormhole's throat, holding it open for safe passage. While exotic matter sounds otherworldly, hints of its existence can be found in phenomena like the Casimir effect, a subtle and exquisitely precise force observed between closely spaced metal plates in a vacuum. These experiments demonstrate that quantum fields can generate negative energy on small scales, offering a glimmer of hope that exotic matter might be more than just theoretical fantasy. Yet, scaling this effect up to the gargantuan energy levels required for a traversable wormhole presents an almost insurmountable challenge. The quantities of exotic matter necessary to stabilize even a small wormhole could rival the energy output of an entire galaxy, a requirement so colossal that it leaves us marveling at the engineering prowess such a feat would demand. Quantum instabilities, a persistent menace. Even if we could conjure the extraordinary exotic matter needed, wormholes face additional threats from the quantum world. Space-time is not a calm and serene expanse. It is a dynamic, restless sea of quantum fluctuations. These tiny but incredibly persistent disturbances ripple through the universe, and in the confined environment of a wormhole, they could amplify dramatically. Physicists worry that such quantum instabilities might cause a wormhole to collapse spontaneously, even if it were initially stabilized. The energy fluctuations could build up within the wormhole's throat, triggering catastrophic gravitational feedback. These challenges underscore the uneasy fragility of wormholes and the immense sophistication required to maintain their stability. Hawking's radiation and the wormhole dilemma. Adding to this delicate scenario is the potential impact of Hawking radiation, the faint but insistent emission of particles theorized to occur near black holes. If wormholes share similar properties with black holes, and many models suggest they do, they might emit radiation that could erode their structure over time. This gradual decay, imperceptibly slow but inevitably relentless, would eventually render the wormhole impassable. This radiation effect creates a tantalizing paradox. While wormholes could provide a shortcut through space-time, their very existence might be undermined by the fundamental forces that govern the universe. Could we ever find a way to counteract these effects? Or is the fragility of wormholes an immutable characteristic of their design? Speculative solutions, from brain worlds to quantum mastery. Physicists, ever resourceful and wonderfully creative, have proposed several speculative solutions to the stability conundrum. One thrilling idea comes from string theory, which suggests that our universe might exist as a brain within a higher dimensional space. Wormholes, in this framework, could be stabilized by interactions between these dimensions, using the properties of the extra-dimensional bulk as a support structure. Another dazzlingly bold concept involves using advanced quantum technologies to actively monitor and stabilize a wormhole in real time. This could involve feeding the wormhole with precisely calibrated bursts of energy to counteract instabilities, or employing quantum computers to predict and neutralize dangerous fluctuations. These ideas remain in the realm of speculation, but they highlight humanity's boundless ingenuity in the face of cosmic challenges. Natural wormholes. Cosmic stability in the wild? While most discussions of wormholes focus on artificial constructs, some theories suggest that natural wormholes might already exist in the universe. These could form spontaneously in the chaotic, high-energy conditions of the early cosmos, or through quantum fluctuations in space-time. If such wormholes exist, they might possess intrinsic stability mechanisms we have yet to understand. However, finding natural wormholes would be an almost unimaginable task. Their presence might be inferred through unusual gravitational lensing effects or anomalies in the behavior of light and particles near their mouths. Advanced telescopes and detectors, scanning the cosmos for these subtle signs, could one day reveal the existence of these elusive portals. The emotional weight of fragility. The fragility of wormholes serves as a humbling reminder of the universe's immense complexity and our own limitations. These tantalizing gateways, poised on the knife's edge between collapse and stability, challenge us to push the boundaries of what we know and what we can achieve. The idea that such cosmic marvels could exist, even if fleetingly, fills us with wonder and a deep yearning to explore further. A future worth pursuing. Despite the staggering difficulties, the pursuit of stable wormholes remains one of the most exhilarating frontiers in science. They represent not just a possibility for interstellar travel or time travel, but a deeper understanding of the universe's underlying structure. Could these ephemeral bridges be stabilized? Could we learn to tame the forces that threaten to collapse them? Or are wormholes destined to remain tantalizingly out of reach, forever a testament to the universe's infinite potential? As humanity continues its journey of discovery, wormholes remind us of the delicate balance between possibility and limitation, between the known and the unknown. Stabilizing a wormhole may be one of the most challenging tasks ever envisioned, but the reward, a doorway to the stars and beyond, might just be worth it. The role of exotic matter. Among the many challenges posed by time travel and wormhole theories, one enigmatic concept stands at the heart of these cosmic possibilities: exotic matter. Unlike the matter we encounter in everyday life, atoms, molecules, stars, and planets, exotic matter defies our conventional understanding of the universe. With properties that include negative energy density and negative mass, exotic matter could be the crucial ingredient needed to stabilize wormholes, enable time loops, and unlock the mysteries of space-time manipulation. But what is exotic matter, and how might we create or harness it? Defining exotic matter. Exotic matter refers to any form of matter that exhibits properties contrary to those found in ordinary, baryonic matter. The most notable characteristic of exotic matter is its negative energy density. In simple terms, this means that instead of exerting an attractive gravitational force like normal matter, exotic matter exerts a repulsive force. This property makes it a theoretical candidate for counteracting the intense gravitational forces that would otherwise cause a wormhole to collapse. Negative energy density also leads to fascinating possibilities. For example, exotic matter could allow for regions of space-time to be warped in ways that would enable faster-than-light travel or the creation of closed time-like curves. These extraordinary effects make exotic matter a cornerstone of theoretical discussions surrounding time travel and wormholes. Theoretical foundations of exotic matter. The idea of exotic matter arises naturally from several areas of physics. 1. Casimir effect. One of the most well-known phenomena suggesting the existence of negative energy is the Casimir effect, a quantum mechanical phenomenon observed between two uncharged, parallel metal plates placed very close together in a vacuum. The energy density between the plates is slightly lower than the surrounding space, creating a measurable attractive force. While the Casimir effect demonstrates negative energy density on a microscopic scale, it provides a glimpse into the potential for exotic energy in the universe. 2. Quantum field theory. In quantum field theory, the vacuum is not truly empty, but teeming with virtual particles that pop into and out of existence. These fluctuations can create temporary regions of negative energy, suggesting that exotic matter might arise naturally in certain extreme conditions, such as near black holes or in high-energy particle collisions. 3. General relativity. Exotic matter fits into the framework of Einstein's equations of general relativity, which describe how mass and energy warp space-time. In certain solutions to these equations, negative energy is required to stabilize structures like wormholes or to sustain a warp bubble for faster-than-light travel. Exotic matter and wormholes. To understand why exotic matter is essential for wormholes, consider the intense gravitational forces at a wormhole's throat. The natural tendency of space-time is to close these tunnels, making them impassable. Exotic matter, with its negative energy density, could act as a kind of anti-gravity, pushing outward and preventing collapse. This stabilization would allow for traversable wormholes, potentially connecting distant regions of space-time or even enabling time travel. Kip Thorne and his colleagues famously demonstrated that exotic matter is theoretically necessary to hold a wormhole open. Their calculations showed that even a small traversable wormhole would require a significant amount of negative energy to counteract gravitational forces. The challenge lies in generating and maintaining this negative energy on a macroscopic scale. Exotic matter and time travel. Exotic matter plays a critical role in several time travel scenarios. 1. Closed time-like curves, CTCs. Exotic matter could enable the creation of closed time-like curves, theoretical loops in space-time that allow objects to travel back to their own past. By bending space-time in specific ways, negative energy could create the conditions needed for these loops to form, opening the door to backward time travel. 2. Warp drives. The Alcubierre warp drive, a theoretical faster-than-light propulsion system, relies on exotic matter to create a warp bubble that compresses space-time in front of a spacecraft and expands it behind. Without exotic matter, the intense gravitational forces generated by the warp bubble would collapse it, making faster-than-light travel impossible. 3. Temporal wormholes. If one mouth of a wormhole experiences significant time dilation, such as being placed near a massive object or traveling at near-light speeds, the wormhole could function as a time machine, with exotic matter stabilizing its throat. Challenges of generating exotic matter. While the theoretical framework for exotic matter is well developed, the practical challenges of creating or harnessing it are immense. 1. Energy requirements. Producing negative energy on a scale large enough for practical applications would likely require vast amounts of conventional energy. For instance, generating the negative energy needed to stabilize a wormhole might exceed the total energy output of a star. 2. Quantum scale. Negative energy effects observed in phenomena like the Casimir effect occur at microscopic scales and are fleeting. Scaling these effects up to macroscopic levels suitable for wormhole stabilization would require breakthroughs in both quantum mechanics and materials science. 3. Instability. Exotic matter, by its very nature, might be unstable, decaying quickly or interacting unpredictably with normal matter. Containing and controlling exotic matter would demand unprecedented advancements in technology. 4. Unknown properties. Because exotic matter has not yet been observed directly, its exact properties remain speculative. Without experimental data, it is difficult to determine whether exotic matter is truly feasible or if it exists only as a mathematical abstraction. Natural sources of exotic matter? Some researchers speculate that exotic matter might already exist in the universe. naturally occurring in extreme environments such as near black holes. The intense gravitational fields around black holes could create regions of negative energy density, potentially producing exotic matter. Cosmic strings. Hypothetical one-dimensional defects in spacetime, known as cosmic strings, might generate negative energy fields capable of bending spacetime in unusual ways. High-energy particle collisions. Experiments in particle accelerators, such as the Large Hadron Collider, LHC, could produce conditions where exotic matter briefly emerges, offering a glimpse into its properties. The search for exotic matter. Despite the challenges, the search for exotic matter is an active area of research. Advances in quantum computing, particle physics, and cosmology might one day reveal practical methods for generating and manipulating negative energy. The development of technologies to measure and control quantum fluctuations could also provide new insights into the nature of exotic matter. The discovery of exotic matter would be a monumental breakthrough, revolutionizing our understanding of the universe and opening the door to technologies that currently exist only in the realm of science fiction. From stabilizing wormholes to enabling faster-than-light travel, exotic matter represents a tantalizing frontier in the quest to master space-time. The promise and mystery of exotic matter. Exotic matter, with its extraordinary properties and profound implications, remains one of the most intriguing and enigmatic concepts in modern physics. While its existence has yet to be proven, its theoretical potential inspires both scientific inquiry and imagination. If we can overcome the immense challenges of creating and harnessing exotic matter, we may one day unlock the secrets of the universe, bending space and time to our will. As we continue to explore this cosmic mystery, one question persists. Is exotic matter a fleeting dream of theoretical physics, or the key to humanity's greatest leaps forward? The answer, if it exists, may redefine our understanding of reality itself. Time travel ethics. The prospect of time travel carries with it not only profound scientific and technological challenges, but also deep ethical dilemmas. If we were to master the ability to traverse time, the implications would ripple through every aspect of human life, past, present, and future. How would we wield such power? What responsibilities would come with altering the fabric of history or glimpsing the unknown future? Time travel ethics forces us to confront the moral complexities of rewriting the story of existence. Altering the past, a double-edged sword. One of the most immediate ethical concerns with time travel is the impact of changing the past. The idea of traveling back to correct mistakes, prevent tragedies, or bring about a better future is inherently appealing. Imagine preventing wars, curing diseases before they spread, or saving the lives of historical figures whose contributions were cut short. These noble intentions, however, come with unpredictable consequences. The butterfly effect, popularized by chaos theory, suggests that even small changes to the past could have far-reaching and unintended consequences. Altering one event, such as preventing a historical war, might destabilize other events, leading to outcomes that are impossible to predict. A time traveler might inadvertently erase their own existence or cause a timeline to deviate in ways that harm countless others. From an ethical standpoint, does anyone have the right to make decisions that alter the course of history? Who would be qualified to decide which events should be changed and which should remain untouched? These questions highlight the moral complexity of tampering with the past. Even well-intentioned actions could lead to catastrophic results, raising doubts about whether time travel to the past should be attempted at all. Responsibility to future generations. Traveling to the future presents its own set of ethical challenges. If time travelers gain access to knowledge about the future, how should they use it? Should they attempt to warn humanity of impending disasters, or allow history to unfold as it naturally would? Revealing future events could disrupt societal structures, undermine free will, and create a sense of inevitability that stifles human progress. Moreover, if future generations exist, they would have a stake in the decisions made by time travelers. Altering the past or present to benefit the current generation might inadvertently harm those who come later. Balancing the needs of present and future populations becomes a delicate ethical calculus, requiring careful consideration of long-term consequences. The paradox of free will. Time travel raises profound questions about the nature of free will and determinism. If the future can be observed or influenced, does this imply that events are predetermined? Conversely, if the past can be altered, does this mean that history is fluid and subject to constant change? These questions challenge our understanding of agency and moral responsibility. For instance, if a time traveler witnesses an inevitable future catastrophe, are they morally obligated to prevent it? If they succeed, would they be interfering with the natural course of history or fulfilling a predestined role in ensuring humanity's survival? These paradoxes blur the lines between fate and choice, forcing time travelers to navigate uncharted ethical territory. Ownership of time travel technology. The development of time travel technology raises pressing questions about who should control it. Should time travel be the domain of governments, scientific institutions, or private corporations? Each scenario presents unique ethical risks. Governments might exploit time travel for political or military advantage, while corporations could use it for profit, potentially disregarding the broader implications for humanity. A centralized authority might impose strict regulations to prevent misuse, but this approach risks concentrating too much power in the hands of a few. Decentralized access, on the other hand, could lead to chaos, with competing interests vying to reshape history according to their own agendas. Establishing an ethical framework for time travel governance would be essential to ensure that the technology is used responsibly. The ethics of non-interference. Some theories, such as the Novikov self-consistency principle, suggest that time travelers might be unable to alter events in ways that create paradoxes. If true, this would impose natural limits on the ethical dilemmas associated with changing the past. However, even within a self-consistent framework, time travelers might influence events in subtle ways, raising questions about the morality of interference. One ethical approach is the principle of non-interference, similar to the prime directive in science fiction. Under this philosophy, time travelers would observe but not interfere, allowing history to unfold as it naturally would. While this approach minimizes the risk of unintended consequences, it also raises questions about whether inaction in the face of preventable suffering is morally defensible. Time travel and personal ethics. Time travel is not just a societal issue, but a deeply personal one. If individuals could travel through time, they would face unique ethical dilemmas. Would it be ethical to revisit loved ones who have passed away, even if it meant disrupting the timeline? Would using time travel for personal gain, such as acquiring wealth or knowledge, be morally acceptable? Personal ethics also extend to the question of responsibility. Time travelers, by virtue of their unique position, would possess knowledge and power far beyond that of ordinary individuals. This privilege carries immense responsibility to use such power wisely and selflessly, avoiding actions that prioritize personal interests over the greater good. The ethics of observation. Time travel technology could enable unprecedented opportunities for observation, allowing humanity to witness historical events firsthand or study the future without altering it. However, even observation raises ethical concerns. Should individuals have the right to observe private moments in history, or would this violate the privacy and dignity of those being observed? Should certain events, such as personal tragedies or sacred rituals, be off limits to time travelers? Moreover, the act of observation itself might influence events. In quantum mechanics, the observer effect demonstrates that the mere act of measuring a system can alter its state. If similar principles apply to time travel, the presence of an observer could subtly change the course of history, even if no direct action is taken. The ethical implications of alternate timelines. If time travel creates alternate timelines, as suggested by the multiverse hypothesis, new ethical questions arise. Would these alternate timelines be considered as real and valuable as the original? If a time traveler creates a branch where a tragedy is averted, does that branch have the same moral weight as the original timeline? Conversely, if an alternate timeline leads to unintended suffering, does the time traveler bear responsibility for it? These questions challenge our traditional notions of morality, which are often rooted in a single, linear reality. In a multiverse, ethical frameworks might need to account for the existence of multiple, equally valid versions of history. Lessons from science fiction. Science fiction has long explored the ethical dimensions of time travel, offering cautionary tales and thought experiments that illuminate the challenges of wielding such power. Stories like The Butterfly Effect and 12 Monkeys highlight the unintended consequences of altering history, while Doctor Who and The Terminator examine the moral complexities of intervention and responsibility. These narratives often emphasize the importance of humility and caution in the face of time travel's immense potential. They remind us that the ability to manipulate time does not absolve us of ethical responsibility, but magnifies it toward a code of temporal ethics. If time travel ever becomes a reality, humanity will need a robust code of temporal ethics to guide its use. Such a code might include principles like non-interference, limiting actions that alter the course of history unless absolutely necessary; transparency, ensuring that decisions about time travel are made openly and democratically; responsibility, prioritizing the well-being of all affected parties, including future generations; accountability, holding time travelers responsible for the consequences of their actions. Developing such a framework will require input from ethicists, scientists, philosophers, and policymakers, as well as a profound understanding of the complexities of time and causality. A timeless question. The ethics of time travel compel us to confront some of the most profound questions about our values, responsibilities, and aspirations. If we gain the ability to manipulate time, how will we choose to wield it? Will we act as stewards of history, respecting the intricate web of causality, or succumb to the temptations of power and personal gain? Ultimately, the ethical dilemmas of time travel remind us that with great power comes great responsibility. As we dream of transcending time's boundaries, we must also strive to ensure that our actions reflect the best of humanity, guided by wisdom, compassion, and an unwavering commitment to the greater good. The speed of light barrier. At the heart of Einstein's theory of relativity lies a seemingly unbreakable cosmic speed limit. The speed of light, approximately 299,792 kilometers per second, 186,282 miles per second, in a vacuum. This fundamental constant governs the behavior of matter, energy, and information in our universe, forming a cornerstone of modern physics. But for those dreaming of time travel and interstellar exploration, the speed of light presents a formidable barrier. What does this limit mean for the possibility of time travel, and are there ways to work around it? Why the speed of light is a limit. The speed of light represents more than just the maximum velocity at which light travels. It's a universal constraint embedded in the fabric of space-time itself. According to Einstein's special theory of relativity, as an object approaches the speed of light, its relativistic mass increases. This means it requires exponentially more energy to accelerate, and at the speed of light, the energy required becomes infinite. For any object with mass, reaching or exceeding this speed is theoretically impossible. Additionally, relativity predicts that time behaves differently for objects traveling at or near the speed of light. A phenomenon known as time dilation causes time to slow down for the traveler relative to an outside observer. While this effect allows for one-way time travel into the future, breaking the speed of light barrier to travel backward in time remains beyond current scientific understanding. The relativity of time and space. Special relativity revolutionized our understanding of time and space, showing that they are not separate entities but interconnected dimensions forming the fabric of space-time. This framework underpins why the speed of light is a hard limit. It is not just the velocity of light, but the maximum speed at which information, causality, and energy can propagate through space-time. Imagine a beam of light traveling through space. It moves at the speed of light because photons, the particles of light, are massless. For objects with mass, like humans or spacecraft, this limit becomes an insurmountable wall, preventing them from reaching the velocities needed for faster-than-light (FTL) travel or direct time manipulation. Challenges of breaking the barrier. Breaking the speed of light barrier would require overcoming immense physical constraints. 1. Infinite energy requirement. As an object approaches the speed of light, its kinetic energy grows without bounds. To exceed this speed, a hypothetical spacecraft would require an infinite energy source, something far beyond the capabilities of any conceivable technology. 2. Causality violations. Exceeding the speed of light could disrupt the fundamental cause and effect relationships that govern the universe. FTL travel or communication might allow information to arrive before it was sent, creating paradoxes that challenge our understanding of physics. 3. Space-time instabilities. Any attempt to break the speed of light might distort space-time in unpredictable ways. The creation of extreme gravitational fields, singularities, or other anomalies could threaten the integrity of the universe itself. Theoretical workarounds. Can we cheat the limit? While the speed of light appears to be a universal constraint, physicists have proposed several theoretical methods for sidestepping it without violating the laws of relativity. 1. Wormholes. Wormholes, or Einstein-Rosen bridges, provide a hypothetical shortcut through space-time, allowing travelers to bypass the vast distances of normal space. By folding space-time, a wormhole might enable faster-than-light travel between 2 points without breaking the speed of light barrier locally. 2. Warp drives. The Alcubierre warp drive, proposed in 1994, suggests compressing space-time in front of a spacecraft and expanding it behind, creating a warp bubble. Inside this bubble, the spacecraft would remain stationary relative to its local space-time, avoiding the energy and causality issues associated with FTL travel. While theoretically plausible, the warp drive requires exotic matter with negative energy density to stabilize the bubble. The energy demands for such a device are currently astronomical, though refinements to the model have reduced the theoretical energy requirements. 3. Tachyons. Tachyons are hypothetical particles that always travel faster than light. If they exist, tachyons could theoretically provide a mechanism for FTL communication or travel. However, their existence remains speculative, and incorporating them into the framework of relativity poses significant challenges. 4. Quantum tunneling. In quantum mechanics, particles can occasionally tunnel through energy barriers faster than light might suggest, although this does not violate causality or relativity. While quantum tunneling occurs on microscopic scales, some researchers speculate about whether similar effects could be harnessed from macroscopic objects. 5. Folding spacetime. Advanced theories in string theory and extra dimensions propose that spacetime might have hidden geometric properties that allow for shortcuts or folds. If these properties could be manipulated, it might enable travel across vast distances without exceeding the speed of light. Faster than light and time travel. Exceeding the speed of light is closely tied to the concept of time travel. According to Einstein's general relativity, faster than light travel could, in theory, allow an object to move backward in time. This is because the relationship between time and space changes dramatically at such speeds, potentially creating closed time-like curves. However, these ideas remain speculative and are often accompanied by paradoxes, such as the grandfather paradox, where altering the past creates logical contradictions. Resolving these paradoxes would require new physics or a deeper understanding of how causality operates in a relativistic framework. Practical implications. The speed of light barrier imposes significant limitations on interstellar exploration. Even traveling at a significant fraction of light speed, reaching the nearest star systems would take decades or centuries. For example, at 10% of the speed of light, a spacecraft would take over 40 years to reach Proxima Centauri, the nearest star system to Earth. While technologies like nuclear propulsion, solar sails, or antimatter engines might one day allow for near-light speed travel, true faster-than-light travel remains firmly in the realm of theoretical physics. Overcoming this barrier would require a fundamental shift in our understanding of the universe. Philosophical implications. The speed of light barrier also carries profound philosophical implications. It imposes a cosmic limitation on humanity, emphasizing the vastness of the universe and the smallness of our existence. Yet, it also challenges us to innovate, dream, and push the boundaries of what is possible. If the speed of light cannot be broken, it forces us to confront the reality of time and space as unyielding constants. But if loopholes exist, it opens up extraordinary possibilities for exploration, communication, and the understanding of existence itself. A glimpse into the future. While the speed of light may remain an unbreakable limit for now, humanity's journey into the cosmos is far from over. Through innovations in propulsion, quantum technologies, and space-time engineering, we may one day find ways to approach the barrier, or even bypass it altogether. The speed of light is not just a challenge. It is a beacon, inspiring us to reach for the stars and explore the limits of our knowledge. Whether or not we ever break it, the pursuit itself is a testament to the boundless curiosity and resilience of the human spirit. The mystery of tachyons. Among the most tantalizing ideas in theoretical physics is the concept of tachyons, hypothetical particles that travel faster than the speed of light. If they exist, tachyons could revolutionize our understanding of the universe, opening pathways to faster-than-light communication, quantum breakthroughs, and even time travel. Yet, these elusive particles remain firmly in the realm of speculation, challenging physicists to reconcile their theoretical properties with the known laws of nature. What are tachyons? The term tachyon comes from the Greek word tachys, meaning swift. First proposed in 1962 by physicists Gerald Feinberg and others, tachyons are unique in that their speed is always greater than the speed of light. Unlike normal particles, dubbed bradyons, or particles of light, called luxons, tachyons would possess imaginary mass, a concept derived from mathematical solutions to Einstein's equations. Tachyons are theorized to behave in peculiar ways. 1. Infinite speed at zero energy. As a tachyon loses energy, its speed increases, approaching infinity. This is the opposite of how normal particles behave, where more energy results in greater speed. 2. Complex momentum. The momentum of a tachyon would be described using imaginary numbers, a mathematical property that does not align with our everyday experiences but fits into advanced theoretical frameworks. 3. Causality challenges. Since tachyons move faster than light, their effects could theoretically precede their causes, leading to violations of causality, where an event's outcome influences its origin. These unique properties make tachyons fascinating to study, but they also raise significant challenges for integrating them into the known physical world. Tachyons and relativity. Einstein's theory of relativity, the cornerstone of modern physics, prohibits any object with mass from accelerating to or beyond the speed of light. This limitation arises because, as an object approaches the speed of light, its relativistic mass increases, requiring infinite energy to reach light speed. Tachyons, however, are theorized to start beyond the speed of light and never slow down to subliminal speeds, effectively sidestepping this restriction. Mathematically, tachyons appear as solutions to Einstein's equations in certain contexts, especially in quantum field theory and string theory. Their existence would not necessarily violate relativity, but their peculiar properties, particularly their implications for causality, pose significant theoretical challenges. Implications of tachyons. If tachyons exist, their discovery would have profound implications for physics, technology, and our understanding of time and space. 1. Faster-than-light communication. Tachyons could theoretically be used to send information faster than light, enabling instant communication across vast cosmic distances. This could revolutionize fields like astrophysics and space exploration, eliminating the delay inherent in light-speed signals. 2. Time travel. The superluminal nature of tachyons suggests they could travel backward in time, creating the potential for time loops or retrocausal effects. For example, a tachyon-based signal sent into the past could provide information to influence future decisions, raising philosophical and ethical questions about free will and determinism. 3. Quantum physics and entanglement. Tachyons could shed light on the mysterious phenomenon of quantum entanglement, where particles appear to influence each other instantaneously, regardless of distance. Understanding tachyons might bridge the gap between relativity and quantum mechanics, offering a unified framework for the universe's laws. Tachyons and string theory. In string theory, a leading candidate for unifying quantum mechanics and general relativity, tachyons play an intriguing role. Early versions of string theory predicted tachyons as fundamental components of the universe, but their presence often indicated instability in the model. Over time, theorists refined these models, reducing the need for tachyons while retaining some of their mathematical properties. Even in modern string theory, tachyons are occasionally used to describe transitions between stable and unstable states of energy, contributing to our understanding of quantum fields and the early universe. Have tachyons been detected? Despite decades of speculation, there is no direct experimental evidence for tachyons. Their properties make them incredibly difficult to detect, as their interactions with normal matter would be minimal. However, several indirect searches and experiments have provided tantalizing hints. 1. High-energy physics experiments. Particle accelerators like the Large Hadron Collider, LHC, have searched for signs of tachyons in high-energy collisions, though no definitive evidence has been found. 2. Cosmic rays. Some researchers have speculated that anomalies in cosmic ray data could be attributed to tachyons, though alternative explanations often prove more likely. 3. Quantum experiments. Certain quantum effects, such as the tunneling of particles through energy barriers, exhibit behavior reminiscent of faster-than-light phenomena. While not definitive evidence of tachyons, these effects suggest the need for further study. Challenges and controversies. The concept of tachyons is not without its detractors. Critics argue that the lack of experimental evidence and the reliance on mathematical abstractions make tachyons more of a theoretical curiosity than a physical reality. Additionally, the causality violations associated with tachyons challenge our fundamental understanding of time and the universe's structure. Some physicists believe that tachyons, if they exist, may operate in realms entirely separate from our observable universe, making them effectively undetectable. Others propose that the equations predicting tachyons might point to deeper, as yet unknown phenomena rather than the existence of faster-than-light particles. Tachyons in popular culture. Tachyons have become a staple of science fiction, appearing in stories as diverse as Star Trek, Watchmen, and Doctor Who. Often depicted as the key to faster-than-light travel or time manipulation, tachyons serve as a narrative device to explore themes of causality, destiny, and the nature of reality. While these depictions often stretch scientific plausibility, they underscore the enduring fascination with tachyons and their potential to reshape our understanding of the universe. The future of tachyon research. Although tachyons remain hypothetical, advances in physics and technology may one day provide the tools needed to test their existence more thoroughly. The intersection of quantum mechanics, relativity, and string theory continues to yield surprising insights, suggesting that the universe's true nature may be far stranger than we currently imagine. If tachyons are discovered, they could unlock a new era of scientific exploration, offering solutions to some of physics' most enduring mysteries. Until then, they remain a compelling symbol of humanity's quest to push beyond the limits of the known and into the uncharted realms of the cosmos. Time travel and the human brain. Time travel, as a concept, is often discussed in terms of advanced technology, physics, and cosmic phenomena. Yet, one of the most fascinating and overlooked aspects of time travel is its potential connection to the human brain. How does our brain perceive time? Could it serve as a natural time machine, allowing us to explore alternate realities, revisit the past through memory, or even glimpse the future? By examining the brain's relationship with time, we uncover profound insights into the mysteries of human consciousness and its potential ties to time travel. The brain's perception of time. The human brain is a masterful timekeeper. It enables us to process events sequentially, measure durations, and anticipate future outcomes. These abilities are mediated by complex neural networks and structures, including 1. The prefrontal cortex. Responsible for higher-order thinking and planning, the prefrontal cortex allows us to simulate future scenarios, imagine consequences, and make predictions. This mental time travel enables us to project ourselves into potential futures, a skill that has been critical for human survival. 2. The hippocampus. The hippocampus plays a central role in memory formation and retrieval. Through memory, we revisit the past, reconstructing events and experiences in remarkable detail. This ability creates a subjective sense of traveling to another point in time. 3. The cerebellum and basal ganglia. These regions are involved in timing and rhythm, helping us perceive the passage of time and coordinate actions in sync with our environment. 4. The default mode network, DMN. This network, active during periods of rest and introspection, is thought to facilitate daydreaming, imagination, and the mental reconstruction of past and future events. It is a key player in our ability to experience subjective time. Memory as time travel. Memory is perhaps the most tangible example of time travel within the human brain. Through memory, we can mentally revisit moments from our past, reliving emotions, sensations, and experiences. This process, while not physical time travel, demonstrates how the brain creates a subjective sense of moving backward in time. Interestingly, memory is not a perfect replay of past events. Instead, it is a reconstructive process, meaning that each act of remembering alters the memory itself. This malleability of memory raises intriguing questions about the reliability of our personal histories and the brain's ability to rewrite the past. Some researchers suggest that memory and imagination are deeply interconnected. The same neural circuits that allow us to recall the past also enable us to envision the future. This overlap highlights the brain's role as a temporal simulator, capable of spanning time in both directions. Déjà vu, a glimpse of time loops? Déjà vu, the eerie sensation of having already experienced a current moment, is one of the brain's most enigmatic phenomena. While often dismissed as a glitch in memory processing, some researchers speculate that déjà vu could represent a deeper connection to time. One hypothesis is that déjà vu arises from mismatches between short and long-term memory systems, creating the illusion of familiarity. However, others have proposed more speculative explanations, such as quantum effects in the brain or fleeting glimpses of alternate realities. Could déjà vu be a natural form of temporal perception, hinting at hidden dimensions of time? Premonitions and future perception. Premonitions, the feeling of foreseeing future events, are another phenomenon that links the brain to time travel. While mainstream science often attributes premonitions to coincidence, pattern recognition, or subconscious processing, some studies suggest that the brain may possess a limited ability to predict future outcomes. For example, experiments in presentiment have shown that physiological responses, such as changes in heart rate or skin conductance, sometimes occur seconds before an unpredictable event. These findings challenge conventional notions of causality, raising the possibility that the brain might interact with time in ways we do not yet understand. Time perception in altered states. Altered states of consciousness, such as those induced by meditation, psychedelics, or sleep, offer intriguing insights into the brain's perception of time. In these states, time often feels distorted, slowing down, speeding up, or even appearing to stand still. 1. Dreams and lucid dreaming. In dreams, the brain constructs entire narratives that often feel temporally inconsistent. A few minutes of real-world time can translate to hours or days in the dream world. Lucid dreaming, where the dreamer becomes aware of the dream, sometimes includes deliberate manipulation of dream time, hinting at the brain's potential for temporal flexibility. 2. Psychedelic experiences. Users of substances like LSD, psilocybin, or DMT frequently report profound time distortions. Some describe experiencing eternity or reliving moments from the past with vivid clarity. These altered perceptions suggest that the brain's sense of time is not fixed, but highly adaptable. 3. Meditation and flow states. Deep meditative states and flow experiences often produce a sense of timelessness, where the present moment expands and past and future concerns fade away. These states highlight the brain's ability to transcend linear time, focusing instead on an eternal now. The quantum brain hypothesis. Some researchers propose that the brain may operate, at least in part, on quantum principles. Known as the quantum brain hypothesis, this idea suggests that quantum effects, such as superposition and entanglement, could influence neural processes. If true, the brain might have access to non-local information, including glimpses of the past or future. Quantum theories of consciousness are highly speculative but fascinating. They raise questions about whether the brain's temporal abilities could extend beyond linear time, tapping into a deeper, multidimensional reality. Neural time machines. Could the brain enable actual time travel? Theoretical physicists and neuroscientists alike have speculated about whether the brain could play a role in physical time travel. While current science offers no direct evidence, the following possibilities are intriguing. 1. Artificial stimulation of time perception. Advances in neuroscience and brain-computer interfaces could one day allow us to artificially manipulate time perception, creating the illusion of time travel or enhancing memory and prediction capabilities. 2. Accessing alternate realities. If the multiverse exists, the brain might serve as a portal to alternate timelines. Through advanced technologies or altered states, it could become possible to explore these realities mentally, if not physically. 3. Consciousness as a time traveler. Some speculative theories suggest that consciousness itself might be capable of transcending time. Near-death experiences and other anomalous phenomena have been interpreted by some as evidence of consciousness operating outside the constraints of physical time. Ethical implications of brain-based time travel. If the brain's temporal abilities could be enhanced or harnessed, it would raise significant ethical questions. Who would have access to such technologies? How would they be regulated? Could they be misused to alter memories, predict behaviors, or manipulate perceptions of time? These questions highlight the need for careful consideration of the societal and personal implications of unlocking the brain's time travel potential. The brain, nature's time machine. The human brain, with its remarkable ability to reconstruct the past and imagine the future, serves as a natural time machine. While it cannot physically transport us through time, its capacity for mental time travel shapes how we experience life, make decisions, and understand the world. By studying the brain's relationship with time, we gain deeper insights into the nature of consciousness, reality, and our place in the universe. As science and technology advance, the line between mental and physical time travel may blur. Whether through enhanced memory, predictive modeling, or quantum breakthroughs, the brain's connection to time offers a glimpse of possibilities that are as profound as they are mysterious. The nature of reality and time travel. Time travel, at its core, is not merely a question of technology or physics. It is an exploration of the very nature of reality. To understand how time travel might work, or whether it is even possible, we must first grapple with profound questions about the universe itself. What is time? Is reality fixed or fluid? Can multiple realities exist simultaneously? These questions lie at the intersection of science, philosophy, and metaphysics, challenging us to rethink our understanding of existence. Time as a dimension of reality. Einstein's theory of relativity fundamentally altered our perception of time, showing that it is not an independent, unchanging backdrop, but a dynamic dimension woven into the fabric of space-time. Time, like space, can be stretched, compressed, and curved. This malleability suggests that time is not absolute but relative, dependent on an observer's motion and position in a gravitational field. If time is a dimension, then the past, present, and future may all coexist in a four-dimensional block universe model. In this view, every moment exists simultaneously, and time travel becomes a matter of navigating this pre-existing structure. While this idea aligns with the mathematics of relativity, it raises profound questions about free will, determinism, and whether reality is fixed or mutable. The illusion of the present. Our perception of time as a flowing sequence of events, the arrow of time, is closely tied to entropy, as dictated by the second law of thermodynamics. Entropy increases as systems move from order to disorder, creating the appearance of a one-way progression from past to future. However, some physicists argue that this arrow of time is a byproduct of our limited perspective. From a broader vantage point, time might not flow at all. The distinction between past, present, and future may be an illusion created by human consciousness. This raises intriguing possibilities. If time is not inherently linear, could we step outside our perception of time to access other moments? If the present is not a universal truth, but a subjective experience, time travel might be less about bending reality and more about expanding awareness. Multiverse and alternate realities. The multiverse hypothesis adds another layer of complexity to the nature of reality. If multiple universes exist, each with its own timeline, then time travel might involve navigating between these realities rather than altering a single, fixed timeline. In this view, every possible version of history and the future exists simultaneously, forming an infinite web of interconnected possibilities. This concept resolves many paradoxes associated with time travel. For example, the grandfather paradox, where traveling back in time to prevent your grandfather's marriage would prevent your own existence, is avoided if such an action creates a new branch of reality. In the multiverse, both timelines could coexist, allowing for free exploration of alternate histories without risking causality violations. Quantum mechanics and the nature of reality. Quantum mechanics, the science of the very small, offers further insights into the nature of time and reality. At the quantum level, particles do not exist in definite states until observed, a phenomenon known as superposition. This uncertainty suggests that the universe is not deterministic but probabilistic, with countless potential realities existing simultaneously. The many-worlds interpretation of quantum mechanics proposes that every quantum event creates a branching timeline, forming a multiverse of parallel realities. Time travel, in this context, might involve shifting between these branches, exploring different outcomes of the same event. Quantum entanglement, where particles remain connected regardless of distance, hints at a deeper, non-local reality that transcends classical notions of time and space. Could this interconnectedness provide a framework for time travel, allowing information or consciousness to move freely across temporal boundaries? The role of consciousness. Some researchers speculate that consciousness itself might play a fundamental role in shaping reality and time. According to the observer effect, the act of observation influences quantum systems, collapsing probabilities into specific outcomes. If consciousness interacts with the quantum realm, it might be able to influence or access different moments in time. This idea is explored in theories like the quantum mind hypothesis, which suggests that the brain's neural processes might involve quantum effects. If true, the mind could serve as a kind of temporal bridge, navigating between past, present, and future states. While speculative, these ideas challenge the traditional separation between the observer and the observed, suggesting that reality is inherently participatory. Simulation hypothesis. Is time programmable? Another provocative theory is the simulation hypothesis, which posits that our reality might be a sophisticated computer simulation. If the universe is programmable, time might be a variable that can be manipulated, paused, or rewound. Time travel, in this context, could involve editing the code of the simulation, accessing different points in the timeline, or even creating entirely new timelines. While the simulation hypothesis remains speculative, it offers a unique perspective on the malleability of time and space. If reality is a construct, then the constraints of physics, including the speed of light barrier, might be bypassed by understanding and modifying the underlying structure of the simulation. Time travel and free will. The nature of reality has profound implications for free will. If the block universe model is correct, and all moments exist simultaneously, then the future is already determined, and free will may be an illusion. Time travel in such a universe would involve exploring pre-existing paths rather than creating new ones. In contrast, the multiverse and quantum models suggest a more flexible reality, where choices create new branches of existence. Time travelers in this framework could influence their own futures and the fates of others, raising ethical questions about responsibility and the morality of altering reality. The fabric of reality, unified theories, and time. The quest to understand time travel is deeply connected to the search for a theory of everything, a unified framework that reconciles general relativity and quantum mechanics. Such a theory would provide a deeper understanding of space-time, energy, and matter, potentially revealing new ways to manipulate reality. String theory, loop quantum gravity, and other advanced models suggest that space-time might be granular, composed of discrete units at the smallest scales. If time is quantized, it might be possible to navigate these units like stepping stones, providing a physical basis for time travel. Philosophical implications of time travel. The exploration of time travel forces us to confront profound philosophical questions about the nature of existence. Is reality deterministic or probabilistic? If the future is fixed, time travel might be limited to observation. If it is fluid, travelers could influence the course of events. What is the role of the observer? If consciousness shapes reality, time travel might be as much a mental journey as a physical one. Does time have a beginning or end? Understanding the origins of time could provide insights into its ultimate nature and whether it can be traversed. A universe beyond time. As we delve deeper into the nature of reality, time travel emerges not just as a scientific challenge, but as a profound exploration of existence itself. It compels us to question the boundaries of time, space, and consciousness, revealing a universe that is far more intricate and mysterious than we can currently comprehend. While time travel remains speculative, its study expands our understanding of the cosmos, pushing the limits of human imagination and ingenuity. Whether or not we ever master the ability to traverse time, the journey to understand its nature will continue to inspire us, illuminating the deepest truths about ourselves and the universe. Paradoxes of time travel. Time travel, while an exciting concept, is fraught with logical and physical dilemmas that challenge our understanding of causality, free will, and the structure of reality. These contradictions, known as paradoxes, arise when the normal flow of cause and effect is disrupted by moving backward or forward through time. Understanding these paradoxes is not just a theoretical exercise. It is essential to determining whether time travel could ever be a practical reality. The grandfather paradox. Perhaps the most famous and widely discussed time travel paradox, the grandfather paradox, involves traveling back in time and interfering with events that would prevent your own existence. Imagine going back in time to stop your grandfather from meeting your grandmother. If you succeed, your parents would never be born, and consequently, neither would you. But if you were never born, how could you have traveled back in time to interfere in the first place? This paradox creates a logical contradiction that seems to make backward time travel impossible. It also raises questions about the nature of causality and whether the universe allows for such disruptions. Some solutions, such as the Novikov self-consistency principle, suggest that events in a time travel loop must be self-consistent, meaning that any actions you take in the past would have already happened, ensuring that the timeline remains intact. The bootstrap paradox, also known as the ontological paradox. The bootstrap paradox involves an object, piece of information, or person that exists without a clear origin. For instance, imagine you receive the blueprints for a revolutionary invention from a time traveler. You build the invention and later travel back in time to give the blueprints to your past self. In this scenario, where did the blueprints originate? This paradox challenges our understanding of causality and creation. It suggests that certain events or objects might exist in a self-contained time loop, with no clear beginning or end. While fascinating, the bootstrap paradox raises profound philosophical and scientific questions about the nature of time and existence. The predestination paradox. The predestination paradox occurs when a time traveler's actions in the past directly cause the event they were trying to prevent, creating a closed causal loop. For example, suppose you travel back in time to stop a historical disaster, but inadvertently cause the very event you intended to prevent. This paradox suggests that attempts to change the past may be futile, as all actions are predetermined within the timeline. Predestination paradoxes imply a deterministic universe where free will is an illusion. They also align with the Novikov self-consistency principle, which posits that time travel cannot alter events in ways that create contradictions. The Polchinski paradox. Proposed by physicist Joseph Polchinski, this paradox involves a scenario where a time traveler sends an object, such as a billiard ball, back in time in such a way that it prevents its own initial journey. For instance, imagine a billiard ball entering a wormhole and emerging in the past, where it collides with its earlier self, deflecting it and preventing it from entering the wormhole in the first place. The Polchinski paradox highlights the challenges of reconciling time travel with the laws of physics, particularly in scenarios involving physical objects and deterministic interactions. Solutions to this paradox often rely on quantum mechanics or alternate timelines to resolve the apparent contradictions. The multiple timeline solution. One way to address time travel paradoxes is through the multiverse hypothesis, or the idea of multiple timelines. In this framework, traveling back in time creates a new branch of reality, leaving the original timeline intact. For example, if you traveled back and prevented your grandfather's marriage, you would create a parallel timeline where you were never born, while your original timeline would remain unchanged. This solution avoids paradoxes by allowing for the coexistence of multiple, independent realities. However, it raises questions about the nature of identity, responsibility, and whether these alternate timelines are as real as the original. The Novikov self-consistency principle. The Novikov self-consistency principle, proposed by Russian physicist Igor Novikov, suggests that time travel is possible, but events within a time loop must be consistent with the overall timeline. In this framework, any actions taken by a time traveler would already be part of history, ensuring that paradoxes cannot occur. For instance, if you traveled back to warn your past self about a mistake, your actions would already be integrated into the timeline. This principle preserves causality by preventing changes that would create contradictions, though it implies that free will may be constrained within time loops. Quantum solutions to paradoxes. Quantum mechanics offers potential solutions to time travel paradoxes by introducing concepts like superposition and probability. In the many-worlds interpretation, every possible outcome of an event creates a new branch of reality, allowing for paradox-free time travel. If you traveled back in time and altered an event, you would simply create a new timeline, avoiding contradictions in your original reality. Quantum entanglement, where particles remain connected regardless of distance, hints at the possibility of non-local interactions that could bypass conventional causality. These quantum effects might provide a framework for understanding time travel without paradoxes, though much remains speculative. Information and causal loops. Time travel also raises questions about the flow of information and its role in causality. For instance, the bootstrap paradox involves information or objects existing in a closed loop, with no clear origin. This challenges our understanding of knowledge, creation, and causality. Some physicists suggest that causal loops might be a natural feature of the universe, governed by principles we do not yet fully understand. Others argue that such loops violate fundamental laws of thermodynamics or logic, making them unlikely in a real-world context. Resolving paradoxes. A unified theory? Resolving time travel paradoxes may require a deeper understanding of the universe's fundamental laws. A theory of everything, uniting general relativity and quantum mechanics, could provide insights into the nature of time, causality, and alternate realities. Concepts like quantum gravity or string theory might reveal mechanisms that allow for time travel without contradictions. Alternatively, the universe might have built-in safeguards to prevent paradoxes, such as the chronology protection conjecture proposed by Stephen Hawking. This idea suggests that the laws of physics naturally prevent time travel to the past, ensuring that causality violations cannot occur. Philosophical implications of paradoxes. Time travel paradoxes force us to confront profound philosophical questions about free will, determinism, and the nature of reality. Is the universe deterministic? If all events are predetermined, time travel might be possible only as a form of observation, with no ability to alter history. What is the nature of causality? Paradoxes challenge our understanding of cause and effect, suggesting that time might not flow linearly, or that causality itself might be an emergent property. Are paradoxes evidence against time travel? Some argue that the existence of paradoxes makes time travel inherently impossible, while others see them as opportunities to refine our understanding of the universe. The allure of paradoxes. Despite their challenges, time travel paradoxes captivate us because they reveal the complexities of time, space, and existence. They challenge us to think beyond conventional boundaries, inspiring scientific inquiry and philosophical exploration. Whether or not time travel is ultimately possible, the study of paradoxes deepens our understanding of the universe and our place within it. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.